Very good morning, all of you. Thank you so much for joining us, joining in today. So, yeah, I hope my screen is visible. So, I'm Mansi Verma. I'm under the supervision of Dr. Chan, Prof. Adam, Dr. Gafurjan, and Dr. Lim. So, the topic of my study is study of rational problems dealing with uncertainty. So, I'm outline will go like this. So, I'll just begin with the little introduction. So as we know, we use mathematical problems to analyze and visualize the real-world problems from a logical perspective. So while we do that, we actually encounter two kind of issues, like generally. So either it can be complexity or it can be interdeterminacy bought by some parameters involved, like score or something which is not so predictable. So regarding that, we have the whole theory of vagueness, which we call as fuzzy theory, which was developed by Zadeh in 1965. So in general, just want to let you know that the fuzzy theory has been studied in the various fields of mathematics, had it been differential equations or modeling and simulation. So here in our topic, we would like to discuss regarding the rational problem. So before we begin up, I would just like to recall that whenever we have given a functional, we need to when we need to minimize it on an admissible space, and to that problem, like for u is equals to integration of f x ux nebula ux. So this particular problem we got as rational problem. So as I mentioned, the fuzzy theory has been applied in various fields of maths. Sticking back to the racial problem, so if I talk about the applications perspective, so you must have heard about image segmentation, right? So in image segmentation, we actually consider regions and then the boundaries of the contour, and that's how it goes on. But the problem is with the classical system, we consider the strict boundaries. What about the blur boundaries or even the discontinuous function? So in order to work on that, people like Mumford in 1989, they discovered this fuzzy contour thing. So they replaced the normal function approximation image via the fuzzy one. So basically they studied this fuzzy model, which was more realistic as compared to the classical one. But the problem is, even in these problems, like image segmentation or it had been optimal control theory, they all actually assume the existence of minimizer. And you must be knowing that whenever it comes to study racial problem, one of the crucial things we need to take care of is the existence of minimizer. However, there's no such theorem to guarantee the existence of extremum in the fuzzy setting exist. You might ask me that why not just apply the classical one, just fuzzify it? Actually, no, it doesn't work that way, because I saw a lot of properties which hold for the crisp function may not hold for the fuzzy function. So basically, in that terms, we need a theory which can work well. So just to give an example, like the convexity part, so the convexity property of the lower bound differential functions may not hold true for that. So we already got a counter example for that. So basically, I'll just revise my problem statement. We have the fuzzy theory in differential equations ODE, PDE, and in FVP, basically fuzzy rational problems, but they are limited to necessary optimality condition. So there have been a lot of other studies based on different differentiability concepts. However, that clearly indicates there's still a research gap in the fuzzy rational problem. So my objectives are like this. So my objectives are to establish the existence and uniqueness of the solutions by the means of multivariable convexity. That's a concept we will develop and we'll use, and we'll derive the results accordingly. Then my another concern is to actually study it under GS differentiability concept, just to make the space of the admissible solutions wider. I'll give you within the PPT, I'll give you a problem which actually cannot be solved in terms of the Bucklean fusion, which is respect to our classical consideration of fuzzy differentiation. that might not work for some problems. So we also established the existence units under GH differentiability. So there are a lot of notions of differentiability for fuzzy functions. However, GH differentiability is the most common one because it overcomes the limitations of the other. So we also theory is appreciated more if we work under less restrictive, basically less restrictive conditions. So we have also developed theoretical approach to establish the general existence theorem, without resorting to EL equations. So here we will be working with we will be constructing a space of weak derivatives, and then we'll followed by few results, and that then will get into our existence of minimizer. And then I'll also demonstrate the application of the above results. So this is a little background. Just now I've mentioned that the calculus of variations, although has been studied in a lot of applications, but when it comes to reality, a lot of parameters can be not so deterministic, or uncertainties can come up. So to deal with that, we need in the fuzzy sense. So as I mentioned, the fuzzy rational principle, that literally limited to the necessary optimality conditions. So we real no existence theorem or result exists in that sense. So that also has been covered up. So these are the basic definitions. Also, just would like to mention the alpha level set is kind of concept that actually allows us to represent, you can say, with respect to every alpha. So when we define fuzzy set, we basically take the values in 0 and 1. So we fix alphas from 0 to 1, and for respect to every alpha, we get all the x's from the domain where we have defined in the membership mu x, which is greater than or equals to alpha. So that corresponds to a set. Now, yeah, so using the same, we actually define the partial ordering as well. So if the left hand side of the alpha level set is less than or equal to the left hand side of the another alpha level set, so we say this is partially less than. That's how we use this sign. So these are the another set of definitions just to recall. So just to give you a little motivation, as I mentioned that really need to establish the existence of minimizer before we calculate it, so that we can actually reduce the cost of computation and we can work accordingly. So let us consider a motion of a particle which is of mass m. So because it is attached to the spring, so k refers to the spring constant. So let us say we are considering a dissipative system where the energy may lost, or so it's more realistic to represent the Lagrangian in terms of the fuzzy valued function. So we end up getting this energy integral. So basically the difference between the potential and the kinetic energy. So then when we evaluate, so till now, yeah, using the initial constraints, so till now whatever theory I had, I used that. I used real equations and I tried to derive it. So I end up getting C2 sine t. But the problem is the C2 is a real constant. It can vary out. So I cannot actually tell you what is the explicit minimizer for this problem. So that was just to denote, the importance that there is a necessary, we need to get into the existence of minimizer before we try to compute it. So this is a visual problem in fuzzy, which we will be considering. As I mentioned, Euler-Lagrange equation, which so people assume that there exists a minimizer and they solve it using this, but this is just a necessary condition. Now we'll try to derive the existence, but again, as I mentioned, the convexity things and whatever classical tools we had for the visual problem doesn't work well in the fuzzy setting. So for that, I used index sets, and we basically described multivariable. We basically established this concept of multivariable preinvexity, and then I also realized that I don't want the preinvexity in all the variables of my integrand. It can also work well with the last two integrands. So I derived this using the eta function, which actually brings back the elements to the same set, and then applying f tilde over that set gives us a partially ordering less than equals to the individual elements. So similarly, this pre-invex condition helps us to retain a blow bound property. So that's the theorem I was talking about before as well. So using that, we did the existence theorem. Because of the time constraint, I cannot show you the whole proof, but I have included the outline. So yeah. And similarly, we obtained the uniqueness theorem as well for the same. So let us just consider quickly a cost production minimization problem. So here I have a functional which is basically corresponding to a cost function. We need to minimize it. Why? This is a model where a lot of defective products are also produced. So we want to make sure that the cost is cutting. P rho is basically defective fraction of the production. So we need to minimize this integral to get a minimal cost. So there are approaches which actually approximate it. However, the question is same. There's no existence. So here in this to demonstrate, we considered this theta function. We defined it like x tilde minus x star tilde, comma x tilde dot minus x star delta dot, and then I computed it. We proved it that this is actually pre-invex, and then we applied our theorem, which we our results which we derived, and hence we can prove it to be pre-invex. So now, as I mentioned, the GH differentiability is one of the most useful, as it overcomes the limitations of others. So these are the brief of the limitations. So as you can see in the last dot, that it considers a two-way thing, like either of the one can be written as a translation. So that actually leads to this is a problem which we actually cannot solve using the classical using the Buckley-Fielding derivative approach. That's why I need to I had to establish it in the GH differentiability as well. As I mentioned, it is two-way thing. So these are my Euler-Lagrange equations corresponding to that. Then I've established the existence theorem and uniqueness theorem for the same. Now, next thing comes up is, all right, we're never happy with the mathematical theory unless we, kind of reduce it or restrict the strong assumption. So it should work under the weaker assumption. So my next target is to actually deal with the sufficient, to actually derive a sufficient condition with less regularity assumptions and guarantee the existence even without realizing EL. So till then we have derived results, but now I need to generalize it with a more. So let us, just for the motivation, let us consider the simple case of Burger's equation. So if we try to solve it under method of characteristic, we end up getting that even can be any constant. So it can be negative. In case I choose my t equals to -1 by a1, that it may lead to, this term will not be defined, this whole, because the denominator will tend to 0. So what's the thing? Can we have a solution in this case? Definitely we need to have, right? But till now, there's no solution for this. Because as I mentioned, the classical theory doesn't work, and in the fuzzy sense, we do not have the solution. So that motivated me to describe the notions of weak derivatives. So we considered Fp omega, the fuzzy sets which satisfy these conditions, and yeah. So corresponding to that, we proved that. So that space is complete, and then we actually constructed the weak derivative definition. So we say that if I have two fuzzy valued functions, if I can evaluate in them in these terms of integrals, like which comes up to be negative of x tilde xi dot tilde, so basically my y tilde will work as a weak derivative in that sense. So then I completed it, completeness theorem again, because of the lack of time, I couldn't include each and every detail. So then I used, as I mentioned, I cannot use the convexity because it doesn't work well, and it doesn't work in the fuzzy setting. So I derived all the results in the invex domain. So I derived an invex lemma. Then yeah, so these lemmas and then the fuzzy Mazur lemma, these all actually help me to, actually talk about some semi-continuity in the fuzzy functional sense, and then derive my general existence theorem. So yeah, with that, I would like to conclude. So we basically observed that the real world problems like image segmentation problem, or it had been optimality condition, or it had been, the drug delivery case. So in that case, people are actually assuming till today. So we really need this kind of theory which actually assures minimizer instead of assuming it. So we demonstrated its uniqueness and existence by defining the multivariable convexity. Then we further extended it towards our DS, and we also developed a theoretical approach where we can have an existence of minimizer under more relaxed conditions. So that's why we developed the concept of V derivative. We and followed by space and the continuous property, and derive the same result. So we also hope that these can be applied in some other electromagnetism applications. How? Because they actually deal up with weak derivatives, and if we talk about in a realistic way, even now there's no guarantee of the existence of minimizer. So these are my references. So last second is our paper, and we have already it's going, second paper is under the summation. With the third one, we have also submitted it to, and the extended abstract has been submitted to an international conference. So with that, I would like to thank you. Thank you so much for listening to me. Thank you.
Thank you, Mansi. Any question from evaluators or supervisor? Dr. Nick, we can't hear you. Enable you.
Okay, Miss Mercy.
Yes, sir.
You speak too fast. I cannot really get what you say.
Sir, we are given just
okay, no problem. Can you go back to your objective?
Sure.
I just have a few questions.
Just a second, sir. Just a
So
second.
with all
yeah.
those objectives, you have 1, 2, 3, 4, 5,
Right.
5 objectives, right?
Okay.
So until now, what year you are now?
Sorry, sir. So I have completed also. I've shared the mini versions of my results as I couldn't include all the proofs, but I've completed all.
No, what year you are now? What
Sorry.
semester you are now? You have final semester?
Yes, sir. It's my 8th semester.
All right. Okay.
Yes.
So you have completed all these objectives?
Right. Right, sir.
All right. Now go back to your figure with many circle.
Okay. Targets. Yes. Just a second. That is for the general existence theorem, I guess. Yeah. Just a second, sir. Yes, sir.
Yeah, that one. With you introduce the minimizer, right, in your function.
Mm-hmm.
Then you have in the point number 3 that guarantee the existence without resulting. So is it just a quite general question?
Sure.
If you have an equation, right, which has no solution, for example.
Okay.
All right. So let's say if you can introduce the minimizer, so can you still get the solution? Because with the existence of minimizer, you said it's guaranteed the existence of the solution.
Yeah. So you're talking in the way that if on solving EL we do not get a minimizer, that's what you're saying?
I don't get you.
So are you trying to ask me that if we're able to solve the the related Euler-Lagrange equation, and while solving we're not able to get minimizer, in that case can we guarantee that? Is it the question?
My question is, you said if you have an equation and by introducing the minimizer, okay, then those the solution of the equation are guaranteed. That's the point.
Yeah, if it satisfies my general our results set of constraints, that definitely.
Yeah, that's point number 3, right?
Right.
All right. So my question is, if you have an equation,
okay,
that you don't have a solution,
Okay.
But you can find the minimizer. Is it possible to find the minimizer? So in that case, you can still have a solution.
So yeah, so in that case, we can have approximate solutions. And yeah, so for that, we generally apply Jacobi's or, other numerical means. So, but even to make sure that we use that, we need to actually guarantee the existence first, so that we can proceed with that in order to reduce the cost computation. So if we are not sure about the minimizer and we are applying it, so it may cause a lot of cost consumption. So yeah, that's the whole idea.
I don't know it's correct or not, but okay, thank you anyway.
So any more questions?
No,
No,
Right,
we
thank you.
can. I also cannot allow any more questions.
Oh,
Right,
okay.
sorry. Because we
so
are.
you can email me anytime.
Yes, sure. Of course.
All right, thank you.
All right, thank you, Mansi. And I would like to call upon the second presenter, Mamika. And the supervisor is Dr. Atira. Evaluators are Dr. Chen Chui and Dr. Ilham. You may be.
Can you see my screen, Doctor?
Yes.
Oh,
Yeah.
thank you. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning. Today, I would like to present my research. The title is Spectrum and Energy of Commuting and Non-Commuting Graphs for Some Finite Groups. And this is my supervisor committee. And this is the outline of my presentation. Actually, the topic of this research is the connection between graph theory and algebra. More specifically, how algebra helps in the study of the graph. Let me start with the definition of the graph. A graph G denoted by G, V, E, with V is the set of vertex and E is the set of edge. If any pair of vertices Vi and Vj are adjacent, then we write Vi, Vj is element of E. A group G is a set together with an associative binary operation which has an identity such that each element has an inverse. In this research, as the set of vertex is the non-abelian dihedral group of order 2n, where n is equal or is greater or equal to 3, which is defined as the reflection and rotation motions that return a regular n-gon to its original state, with composition as the operation denoted by D2n. And the center of D2n, ZD2n, is either the set of E if n is odd, and or the set of EB n over 2 if n is even. Also, we have the centralizer of every element in D2n. The centralizer of AI is the set of AI, and the centralizer of AIB is these two sets. Now we are moving to the definition of non-commuting and commuting graph. The non-commuting graph on G denoted by gamma G has G minus the center of G as its set of vertex with two distinct vertices VP and VQ joined by an edge whenever VP VQ is not equal to VQ VP. And the commuting graph is the complement of non-commuting graph denoted by gamma bar G. And the set of vertex of commuting graph is the same with the set of vertex of a non-commuting graph. However, the requirement is VP VQ is always equal to VQ VP. Non-commuting and commuting graph can be further associated with the adjacency matrix A, which has entries are equal to 1 if there is an edge between Vi and Vj and 0 otherwise. And the degree of vertex Vi denoted by dVi is the number of vertices adjacent to Vi. Okay, since the non-commuting and commuting graphs are simple graphs, then we can construct the adjacency matrix as the square matrix. Therefore, we can calculate the eigenvalues and the list of eigenvalues as the spectrum of gamma G. And if we take the maximum of absolute eigenvalues, we arrive to the spectral radius of gamma G, which is a non-negative real number and is the smallest disk radius that includes all the eigenvalues of gamma G. One of the most researching topics in the field chemical graph theory is energy of graph. The definition is the summation of absolute eigenvalues. So in graph theory, there is one branch, chemical graph theory, in which there are topological indices and energy of the graph. Researchers extend the study of topological indices to the new definition of graph matrices. As the result of combination between graph matrices and energy of graph, we have degree-based energies. On the other hand, also we have the ordinary energy of commuting and non-commuting graph, and this is the position of our research. Study on degree-based energies is dominated by finding the lower and upper bound of its degrees, its energies. They work on simple finite graphs. Some work in the field of physics, especially to predict the boiling points, heat of vaporization, critical temperatures of alkenes. Some also presented the formula of characteristic polynomial, the formula of energy, and the bound of eigenvalues. Also, they extend the study to the properties of spectral radius, like number 21. And recently, the study of degree-based energies continue to the new definition of matrix. The study of ordinary energy of commuting and non-commuting graph for dihedral group, it can be seen to the number 2, 3, 4, 5, the work in dihedral group, but this is only for adjacency energy, Laplacian energy, and signless Laplacian matrix. And for other type of groups, we can see in number 1 and 6, they work in the non-abelian groups and AC groups. However, to our best knowledge, limited articles have comprehensively discussed the degree-based energy and the spectral radius of commuting and non-commuting graphs for dihedral groups. Therefore, the study aims to determine the degree of vertices and the connectivity of the commuting and non-commuting graphs for dihedral groups. Second, construct 25 type graph matrices. Third, formulate the spectrum and the energy. Fourth, investigate the relationship between the obtained energies and the ordinary adjacency energy and their spectral radius. For the first objective, the first step is we assume the G1 is the set of rotation elements of G2n that are not members of the center, and G2 is the set of reflection elements of G2n. After that, we need to investigate the degree of every vertex and the connectivity of commuting and non-commuting graphs for G is equal to G1 union G2. Also, we need to observe the isomorphism of those graphs with the common type of graphs. The methodology of second objective, from the three properties, degree and isomorphism, adjacency between two vertices, and the definition of degree-based matrices, we are able to construct the 25 graph matrices of gamma G and gamma bar G. And after that, we need to check whether it can be partitioned into several block matrices. And the definition of degree-based energies are: first, maximum degree, minimum degree, sum connectivity, degree sum, Randic matrix, geometric arithmetic, greatest common divisor degree, symmetric deviation degree, vertex Zagreb adjacency, forgotten adjacency, degree exponent, harmonic matrix, atom bond connectivity, degree square sum, first Zagreb, second Zagreb, degree subtraction, inverse sum index, degree exponent sum, misbalance degree, degree exponent subtraction, neighbors degree sum, Randic type is SDI, Sombor matrix, and the latest matrix is Nirmala matrix. For the third objective, from determinant row or column operation and block matrices properties, we formulate the characteristic polynomial of gamma G and gamma bar G, and the roots of characteristic polynomial is the eigenvalues, and we get the spectrum. Eventually, we get the energy of the graphs. For formulating the characteristic polynomial, this theorem 1 is our guideline how to modify the determinant of square matrix. Also, we have lemma 1 because if we have this particular form of determinant, lemma 1 give our simplify the expression of characteristic polynomial as this formula. However, if we don't have that particular form, we still have theorem 2, because in theorem 2, if we have 4 blocks matrices A, B, C, D, then the determinant M is equal to determinant A times D, determinant D minus C, A inverse B. And lemma 2 also very useful, because if we have complete graph on n vertices, directly we know the spectrum of complete graph. For the fourth objective, theorem 3 is the connection between two disconnected components of graph with their energies. So we need to check theorem 3, whether theorem 3 is hold for our results. And then theorem 4 is the adjacency energy of the non-commuting graph. However, we still don't have the adjacency energy, the adjacency energy of commuting graph. So we need to formulate first and determine the spectral radius and investigate the relation between degree-based energies and the adjacency energy and their spectral radius. Since this matrix is based on the degree, so we need these two results from Kasrau, because Kasrau presented the degree of every vertex for non-commuting graph, and also in theorem 6, they gave the isomorphism of non-commuting graph with common types of graphs. And this is our first result. We presented the degree of every vertex in the commuting graph, and if G is equal to G1, the commuting graph is isomorphism with complete graph on M vertices. And if G is equal to G2, the commuting graph is isomorphism with these two graphs. As the example, I pick N is equal to 4, then we have D8 here, and the center is only 2 elements, meaning that the commuting graph has 6 vertices. Using the information of the centralizer, we are able to have the edges, and the non-commuting graph is the complement of commuting graph. Another example, if we have N is odd, this is N is equal to 5, we have D10, and the center only the identity, then the number of vertices is 9, and if G is equal to G1, this is the complete graph on 4 vertices, and if G is equal to G2, this is 5 isolated vertices. As the comprehensive result, I show in this table the energy of non-commuting graph for dihedral group for N is odd. This is for G is equal to G1, G2, and G1 union G2. Also, if N is even, continue until number 25. And for energy of commuting graph, we have red colors here, because the energy of G1 union G2 is equal to energy of G1. Another case, if N is even, the energy of G1 union G2 is equal to the summation of energy of G1 and energy of G2. For the purpose of this final seminar, I would like to present one proving part of degree sum energy, where G is equal to G1 union G2. We have two cases here. Since the nature of dihedral groups, they have different type of center and centralizer of dihedral group. So in this proof, when N is odd, we have the degree of every vertex, and the center if identity, then we have 2n minus 1 vertices. Using the definition of degree sum, we construct the matrix, and we can see here we have 4 blocks matrices as follows, and the characteristic polynomial. Since this form, this determinant is similar with the lemma 1, so we can use the lemma 1 result, and directly we get the characteristic polynomial and also get the spectrum and the degree sum energy. There is one
You have 2 minutes.
Yes, there is one interesting result, because the degree sum energy is equal to the double of degree spectral radius. Okay, for N is odd, we have this expression because one component of commuting graph is isomorphism with complete graph on n-1 vertices, and for n is even, commuting graph consists of disconnected two components G1 and G2. The other 6 type matrices and the non-commuting graph doesn't meet sufficient condition of the above properties. And this is the comprehensive result also from number 1 to 10. And we give the relation between adjacency energy and degree-based energies as follows, and the relation between degree-based energies and their spectral radius. And also another result, the 24-degree-based energies of the commuting and non-commuting graphs for dihedral groups are never an odd integer. It is confirmed from the result from Bapat and Pati. They mentioned that adjacency energy of a simple graph is never an odd integer. As the conclusion, this study presented the spectrum and degree-based energies of commuting and non-commuting graph for dihedral groups. The relation between these energies and their spectral radius and adjacency energy has been provided. It is recommended to study a similar study for other finite groups and also to examine on the same groups in different type of graphs. As the outcome, we have presented some papers in the conferences, and this is our publication, and this is our references. Thank you, Doctor.
Thank you, Mamika.
Thank you.
So any questions?
Yes, for me, how many new results that you have?
How many are? Yes, this.
All those?
From this, Doctor, from the relation between adjacency energy and degree-based energy, we have 50 relations, and also the relation between degree-based energy and their spectral radius.
Okay,
And
all
this.
of these are new, yes?
Yes, this is new, Doctor.
And each of them has proof?
Yes, has proof.
Okay, your thesis must be very thick then. How many
Sorry?
pages, your thesis?
Oh, yeah. Now I have more than 300 pages, Doctor,
Oh,
but
okay.
Dr. Atira told me the solution.
Okay, each of them has proof, yes? So,
Yes.
what is the similarity between the proof of each of your result?
The similarity? Could you explain?
Is there any similar pattern between the proof?
Yes. There is a similar pattern. Because if we see the, let me show the picture. This. Because if we have the commuting graph for n is odd, this is actually 5 isolated vertices. So we have similar pattern of proof in this area, where G is equal to G1, G2.
Okay. So I mean, so many. So you might have like 50 results, 70 results,
Yes.
by using similar pattern. I mean.
Not all similar, Doctor, because every matrix has their special method for formulating the characters polynomial, especially how to modify the determinant to get the characteristic polynomial.
Yeah, I mean, you study case by case, specific
Yes.
examples.
Yes.
And if you study more examples, like 60 examples, then you get 60 new results, yes? Am I correct?
Yes.
So is there any way that you can generalize?
Yes. I can generalize that result at the last result, because this is new idea of using the degree-based energies to the graph related to the groups. So as usually, like researchers work in the ordinary energy using only adjacency matrix. So they mentioned this, and also my result can prove it is.
So your main contribution is which one? Because the list of 25 is just calculation, isn't it? It is new, but it's just calculation. What is your really main contribution?
My main contribution, I conduct the method to get the energy, the eigenvalues of the matrices.
You mean you are using your own new method?
How to modify it, doctor? That is my own method.
Okay, what do you modify? What is the improvement that you made in your method?
Okay. This one, because we have 2n-1 times 2n-1 matrices, and we don't know how to solve it, how to find the determinant. So I use this theorem, and also this theorem 1, to get the characteristic polynomial. But in the first of step, we get the degree of every vertex on the commuting graph for the hydral group. That is also new, doctor. Because without that, we cannot construct the matrices.
Okay. So a new method in terms of that. I mean, do you combine the method to get a new method? I mean.
Yes, I combine it.
Okay, what type of proof that you use in proving each of those 25? Is it by induction or what?
What type of improvement?
What type of proof?
Okay, I take two types of n, where n is odd and where n is even.
And okay, and you prove by direct proof or by induction or by what method?
I'm not sure. Direct method?
Direct method, not induction, yes?
No, not induction. Direct method.
Okay, thank you. That's all for me.
Welcome.
All right. Thank you, Dr. Idham, and also thank you, Namika. I'm sorry that I can't take any more questions. Okay. So I'm going to get to the third presenter, Ahlam Ahmad Al-Harbi. Supervisor is
Yes.
And
yes, I'm here.
Dr. Atira and Dr. Chen. Okay, you may begin any moment.
I will share the screen. So you see my slides?
Yes.
Bismillahirrahmanirrahim. Assalamu alaikum. Good morning. My name is Ahlam Al-Harbi, PhD student in UPM. My supervisor, Prof. Adam Klishman. I will present to you my research entitled The Generalized Cloud Sets in Quasi-Pi Topological Spaces and Some of Their Applications. And my co-supervisor, Dr. Athira and Dr. Sheen. The research plan includes 8 sections, starting with introduction, and then explaining the research problem and its objectives. After that, the purpose study. In addition, the most important result. After that, the conclusion, followed by the presentation of the references list. Introduction. The importance of this science that it's proved a geometric study of irregular shapes and gives accurate result based on number from 0 to 1. And it started when, by Zada in 1965, when he defined the notion of fuzzy sets as follows. A fuzzy set is a pair U and M, where U is a fuzzy set, and M is a function from U to the closed interval 0 and 1. A membership function function for each x element in U. The value M of X is called the grade of membership of X in U and M. After that, Chang in 1968 presented the definition of fuzzy topological space, and it known as follows. A family delta of fuzzy sets is called fuzzy topology if satisfies 3 axioms. Number 1, 0 and 1 element in delta. Number 2, the finite intersection of members of delta is also in delta. Number 3, the arbitrary union of members of delta is also in delta. And the pair X and delta is called fuzzy topological space, FTS for short. From the definition of fuzzy topology appeared the definition of fuzzy pi-topological spaces by Candle in 1989 as the following: a triple X and tau 1, tau 2, where X is non-empty set, and tau 1 and tau 2 are fuzzy topology on X, is called fuzzy pi-topological spaces, and denoted by FPTS for short. All the purpose definition of fuzzy sets, fuzzy topological spaces, and fuzzy pi-topological spaces are considered as the basis for our research. But it is also depend on some types of fuzzy sets, which many scientists contributed to introduce them. They are 4. Number 1, fuzzy beta, paired by Al-Munsif in 1983. A is beta open if A subset of a closure interior closure A. A is fuzzy semi-open if A subset of a closure interior A by Gangley and Sasha in 1986. And A is fuzzy pre-open if A subset of interior closure A by Single and Barkash in 1991, but in 1992 by Single and Rajavanshi, they defined fuzzy alpha set if A subset of interior closure interior A. One of the main pillars in the idea of the research is the definition of generalized closed sets and defined as follows. A fuzzy subset A is called fuzzy generalized closed sets if closure A subset of a U whenever A subset of a U and the U is fuzzy open. So from the first definition, we notice that the generalized closed sets depend on 2 factors. Number 1, the open groups, and number 2, the closure operator. From here, the research idea emerged, which aims to study many applications on them. We will review the idea of the research in detail in the problem statement. So number 2, the problem statement and objectives. First, we define the problem. Many scientists contribute to develop the fuzzy topology and then to develop the fuzzy pi topology. But there is a little contribution to fuzzy pi topological spaces. So our aim to complete the path of the various scholars and to start from where they left off by transferring the concept of generalized closed sets to fuzzy pi topological spaces, and then by applying many concepts on it and contributing to its development. So the importance of this research is evident through it's illustrated by the fact it is contribute to be a references for fuzzy pi topological spaces. So the idea of this research is one of them because it introduced many basic concepts which is not discussing yet on it. So the natural problem statement in research lies in merging the 3 pillars on it, which are fuzzy pi topological spaces, types of fuzzy sets, and the definition of fuzzy generalized closed sets. From the definition of generalized closed sets by Garib and Nourini in 2011 as the following: A is generalized closed if tau j closure A subset of a U whenever A subset on a U, but a U is element in tau I. We want to keep the first factor of the definition fixed on the fuzzy open set in tau I, but making the second factor includes the types beta, semi, pre, and alpha closed from the second topology tau j. So the extended results, many results were defined that we will present to you in the details in the following slides, but in general, the new definition of generalized closed sets were defined, also relationship between them, also some counterexample to explain the relation between them. The objectives. Of our study is the 5 steps. Number 1, the theoreticity and innovation by applying the new idea in research in fuzzy pi topological spaces. Number 2, to contribute and transfer many topics to fuzzy pi topological spaces and make this research as initial references for it. Number 3, to develop the definition of generalized closed sets and transfer it to fuzzy-pi topological spaces. Number 4, to demonstrate the new definition of new separation axiom, compactness, connectedness, regular space, and normal space by using the new definition of generalized closed sets and fuzzy-pi topological spaces. And number 5, several examples and important theorems will be added in every step. Literature review. The following slides include the purpose study, which can be defined into 3 sections. Number 1, the beginning and the development of fuzzy topology and the different types of fuzzy sets. Then the contribution of scientists to improve the concepts of fuzzy generalized closed sets. And finally, the beginning and development of fuzzy-pi topological spaces concepts according to a timeline that started with the scientist Dada in 1965, and he considered the founder of fuzzy science when he defined the fuzzy sets as following, and as we mentioned before in the introduction slides. Then in 1968, Chan developed the theory of fuzzy topological spaces when he defined the definition of fuzzy topological spaces, also as we mentioned before, if the delta fuzzy sets satisfies the 3 axioms. After that, in 1970, Levine was the first to define the notion of generalized closed sets, but in general topological spaces, not in fuzzy topology, in general topology, also as we mentioned before. Then in 1985, Ali Mashhour et al. Applied the concepts of Levine on continuous and open mapping, but in fuzzy topological spaces. So this team considered who was transfer the notion of generalized closed set, but in fuzzy topological spaces. In the following definition, A is fuzzy generalized closed if closure A subset of U whenever A subset of U and the U is fuzzy open set. Then in 1989, Sandel established the fuzzy-pi topological spaces by the definition of fuzzy-pi topological spaces, also as we mentioned before in the introduction slides. Then in 1994, Abu Saya et al. Applied the concepts of fuzzy separation axiom and fuzzy continuity in fuzzy-pi topological spaces. In the same year, is introduced semi-open sets, semi-continuity, and semi-open mapping in fuzzy-pi topological spaces. Then in 1995, and Samaja introduced fuzzy beta open sets and its continuous mapping in fuzzy topological spaces as the following definition. A is fuzzy ij beta open sets if A subset of tau j closure, tau I interior, tau j closure LA. So we notice that closure from the second topology, but the interior from the first topology. In the same year, Candle introduced the concept of separation axioms, continuity mapping, and compactness for fuzzy-pi topological spaces. Then in 1996, Nuh studies the separation axioms in fuzzy-pi topological spaces in terms of a quasi-coincidence, a quasi-neighborhood, and the closure operator. By the following definition, a space x tau 1, tau 2 is called the quasi-T0, for example, if for any 2 distinct points, x and y of an x, there exists a element in the pi topology such that x quasi with an a, but y is not a quasi with an a, or y quasi with an a and the x is not a quasi with an a. Then in 1997, Parasuperminian and Sandram introduced the continuous and open mapping by some types of generalized fuzzy closed sets by the following theorems. Let x and tau and y and sigma be fuzzy topological spaces, and sorry, and the f is function from x to y. Then an f is fuzzy generalized continuous if and only if for every fuzzy closed in a y, the inverse image of it is fuzzy generalized closed in an x. In 2001, the brothers Servestavia applied the compactness concepts in fuzzy-pi topological spaces. In 2004, Johan and Sandram studied generalized closed groups in general pi topological spheres. In 2009, Ahmed and Arthur applied the closed and open mapping on fuzzy semi-open sets. In the same year, Hakim and Latha introduced the new result on closed and open mapping by using alpha open sets as the following theorem. For each U of fuzzy topological space X, U is fuzzy alpha open if and only if there exists fuzzy open set M, such that M is subset of a U and the U subset of interior closure of M. The proof, if we suppose that U is fuzzy alpha open, then U is subset of interior closure interior O, because this is the definition of the fuzzy alpha open sets. Hence, from M is subset of a U, then is subset of interior closure M, where M equal interior of a U, so we satisfy the theorem. In 2011, Garib and Noreen introduced the generalized closed set, but also in pi topological spaces. In 2013, Teek and Jean introduced the concept of intuinistic fuzzy pi topological spaces and introduced different types of open sets in fuzzy pi topological spaces. In 2013, Amin et al. Introduced two notions of fuzzy pairwise T0 in pi topological spaces in the following definition: fuzzy pairwise T0 if and only if for every pair of fuzzy singleton sets X and Y with X is not equal to Y, there exists tau1 open sets or tau2 open sets which contains one of the fuzzy singleton sets and not quasi-coincident with the other. In 2015, Ghazwan and Munir introduced fuzzy delta open set and the relation of some fuzzy open sets and some types of fuzzy delta separation axiom, but in fuzzy topological space. In 2016, Al-Alim et al. Introduced the new types of continuity and openness in fuzzy pi topological spaces. The same team introduced the concepts of IJ semi-open sets and IJ semi-neighborhood system in fuzzy pi topological spaces. He introduced the IJ theta generalized double fuzzy closed sets in double fuzzy pi topological spaces. In 2018, Samir and Al-Muthanna continued the study of the concepts of minulated and the homogeneity in the fuzzy consist. In 2019, Al-Alim et al. Studied the concept of semi-compactness in fuzzy pi topological spaces. Farah and Tahir in the same year studies some basic properties of a tri-alpha open sets in fuzzy pi topological spaces. Finally, in 2020, K and G introduced two notions of regular T0 property in fuzzy topological spaces by using a quasi-coincident sense. Jean and Fahanu introduced fuzzy pairwise compactness in the following definitions: a fuzzy pi topological spaces Z pi I pi j said to be fuzzy pairwise compactness if each fuzzy pairwise open cover of Z has a finite subcover. A flowchart. In the following flowchart, we summarize the purpose studies for the three pillars, which are the fuzzy generalized closed sets, the fuzzy pi topological spaces, and the types of generalized closed sets. Conclusion with our aim in this proposal is to define and introduce some types of generalized closed sets in the new framework of fuzzy pi topological spaces, and number two, apply some basic concepts like compactness, connectedness, and so on. Methodology, we have 8 steps. Number one, the study of some fundamental notion of fuzzy sets. So it's including the essential definition and the theorem to other steps like fuzzy topology, fuzzy pi topology, fuzzy types of fuzzy sets, and so on. Number two, the new types of fuzzy generalized closed sets in fuzzy pi topological spaces will be introduced. They are IJ generalized alpha closed, IJ generalized semi-closed, IJ generalized pre-closed, IJ generalized beta closed, and their complements. then the study of the sum theorems and explain the relation between them. Number 3, new concepts of fuzzy neighborhood.
You have
Wait.
1 minute.
Okay. Number 3, study of neighborhoods. Number 4, compactness. Number 5, connectedness. Number 6, separation axioms. And the regular space, finally, the normal space, also by the new definition of generalized closed sets and classified topological spaces. And we use some abbreviation during this research as in the following tables. The main definition, number 1, the definition of generalized closed sets and classified topological spaces. Here we fixed the first operator on tau I, but leave the second operator closed tau j alpha closure, tau j semi-closure, tau j pre-closure, tau j beta closure. And if we take the complement of this definition, we found IJ generalized alpha open, semi-open, pre-open, and beta open. And also we abbreviated this by OFG psi for all types of generalized open set, and FG psi for all types of generalized closed sets and classified topological spaces. And the following diagram explains the relation between them. And also we found some counterexample to show the conference is not true in general. We have the following example, all of them to show the conference relation between the above definition. Here we have some important theorems. Number 1, the remark, the fuzzy IJ generalized psi closed sets and fuzzy tau I or tau j of generalized closed sets, they are independent, and we give the example to show that, to prove that is true. Theorem for number 1, explain when the fuzzy, the all types of fuzzy generalized psi in Ji subset of the all types of closed fuzzy generalized psi in Ij generalized closed sets, and we prove that. Theorem for number 2, explain where is the equivalent relation hold between fuzzy Ij generalized psi closed sets and tau j psi closed sets in one topology, and we prove that from 1 to 2 and from 2 to 1. Here we prove that the finite union of fuzzy I generalized psi closed sets is fuzzy I generalized closed sets. But in theorem 4.4, we show that the finite intersection is not hold. And the following example is show that D1 and D2 are 1, 2 generalized alpha closed, but their intersection is not. After that, we have the second main definition of fuzzy generalized neighborhood and fuzzy generalized quasi neighborhood by using the definition of the all types of Ij generalized psi closed sets and fuzzy by topological space. And the psi here denoted by alpha, semi, pre, and beta. And also we have the following diagram to explain the relation between them. And this theorem explains the properties of neighborhood by using the fuzzy Ij generalized psi closed sets, and we prove that. Also, we have, if we take the complements, if we prove this theorem also for generalized quasi neighborhood by using a quasi concept as following.
I think you can go to your conclusion.
Okay. And here the properties of closure operator and the closure interior. Here the future plan. The expected result, the new definition of compactness, connectedness, separation axiom, normal and regular space by these definitions of fuzzy generalized closed sets. So the primary goal is to investigate some concepts of fuzzy generalized closed sets and fuzzy by topological spaces. In addition, many applications of these concepts like closure, interior, neighborhood, and so on, study some counterexamples to explain the relation. And now the list of references. And it's my pleasure to contact me on the following addresses. Thank you. And if you have any questions.
All right, thank you, Ahlam. So I'm going to take only one question from evaluators or supervisor.
Okay.
Yes, may I ask?
Yeah, sure.
Yes, Ahlam, first of all, my comment is that you spent too much time on the literature review that you didn't have time to go for your results. Okay, but I have just one question. Can you go to yeah, just slide 11 maybe?
11. Okay, this one.
Yeah.
Mhm.
Okay, so I believe in pure mathematics, we do study a lot of spaces and so on and so forth. Okay, may I know, can you actually describe a little bit to us how would you apply them in terms of mathematics in mathematics or even in real applications?
Okay. We show that in the following diagram. So all the purpose study, can we define it into three sections? Number one, the types of fuzzy sets, and number two, fuzzy pi-topological spaces, and number three, the fuzzy pi-topological spaces. So there are many studies in every section of them. Our aim is to transfer the concepts of fuzzy generalized closed sets and fuzzy pi-topological spaces, and this definitions in the same time based on two factors: the openness and the closure operator. So in the closure operator, we use the purpose study and the fuzzy types and the types of fuzzy sets. So for that, we introduced the new definitions of generalized closed sets by these types of fuzzy sets, but in fuzzy pi-topological spaces. Because as we mentioned before, there is a little studies in fuzzy pi-topological spaces because it's maybe more complex to use two topology. So we can use this and to be references in this slide. So it's a new idea.
Okay, I think we don't have time to explain for the way. Maybe we can go for the next time. Okay, thank you.
All right, thank you, Dr. Chen, for asking, and also Ahlam. All right, so we go to the next presenter, Muhammad Al-Amin, supervisor, Dr. Muhammad Shafi'i, evaluators, Dr. Janti, and also Dr. Wendy. And I would like to remind you that you have 15 minutes for presentation, 5 minutes question and answer.
I think he's talking right now.
Are you talking, Muhammad? Okay, nampak macam dia tak ni.
Muhammad, I think you need to unmute yourself.
Turn on your, saya dah ask to unmute tapi dia tak pasti. Turn on your audio, please.
Problem.
All right, we can hear you. And
You hear me now?
yes.
That's okay. Just 1 minute. Let me share my screen.
All right.
You see my screen now?
Not yet.
Oh, what is that? I don't know why it's not working. Bismillahirrahmanirrahim. Maybe it's due to the net or what's happened. La hawla wa la quwwata illa billah. I don't know what's the problem. La hawla wa la quwwata illa billah. Just 1 minute. Let me check what the problem is.
Okay.
Just 1 minute, please. Okay, because it's not sharing. Let me sign out and then come again. I will leave and sign again. Okay.
All right. So in that case,
Proceed to next presenter dulu lah Nadia.
yeah, yes. Saya risau nanti ada orang ni pula. All right, okay. I think we can proceed to the next presenter. Nur Syairah binti Wahid, the supervisor, Prof. Dr. Nur Rehan, and also evaluators, Dr. Nur Fifah and Prof. Zanaria.
Semua tu dah masuk ke?
Dia tak masuk lagi. Dia tak masuk lagi, dia keluar tadi ada masalah. So,
Bukan Norehan, Dr. Norehan.
tak apa, saya dah record nanti kalau dia minta kita ni teruskan.
Okay, kita boleh start sekarang ke?
Yes, please.
Okay. Okay, Bismillahirrahmanirrahim. Assalamualaikum and a very good morning to everyone. I am Nur Syairah Wahid. So I'll be presenting my research progress, which the title is on boundary layer flow and heat transfer of hybrid nanofluid. Okay, this is the outline for my presentation, where I'll focus more on the flow problems that include cell formulations, method of solution, as well as several of the results that is on the two types of effect. So for just a very brief introduction, in the study, there exists two concepts, which is boundary layer and heat transfer. So for boundary layer, it is actually a thin layer of flowing fluid, whether a gas or liquid, that is very near to the surface. So we are interested in knowing that behavior of that flowing fluid when certain circumstances or effect or conditions is being imposed. And then for the heat transfer, it is the flow of heat in terms of thermal energy due to temperature differences. And there exists three mechanisms, which is conduction, convection, and radiation. So as being mentioned in the title, hybrid nanofluid is being considered in this study. So it is a new generations of nanofluid that is formed by dissolving different types of solid nanoscale particles into the base fluid. So many researchers have claimed that this fluid have a better rheological, thermal network, and synergistic effect properties compared to the traditional mono nanofluid or even the conventional fluid. So this fluid also have a wide application, especially in engineering field, for example, in automobile, in electronic devices, in solar panel, as well as in biomedical industries. And then in all of the flow problems, the radiation effect is one of the effects that will be considered, where it is the process by which the energy in the form of electromagnetic radiation is radiated in all directions by a heated surface. So this study on the effect of thermal radiation is important, especially for the development of thermal energy stations, rockets, satellites, and polymer industries. And these are several investigations that consider the radiation effect towards hybrid nanofluid. Then the second main effect is Magnetohydrodynamic Effect, which is in short is MHD effect. It is a physical mathematical framework on the dynamics of magnetic fields in electrically conducting fluids. So the analysis of MHD in boundary layer flow is essential, for example, in the metallurgical operations and petroleum productions. And these are several recent investigations that consider MHD effect on hybrid nanofluid. So now for the problem statement, it is generally known that hybrid nanofluid is a new class of nanofluids that offers a potential scope for abundant heat transfer application, especially in engineering. Then recent experimental and numerical investigation mostly claim that hybrid nanofluid improve the heat transfer performance of a system. However, there is also a few inconsistent judgment about this due to different combinations of hybrid nanoparticles, the mixing ratio concentrations, the implications with other various effects, as well as the different geometries. Therefore, several different hybrid nanofluid models with different impositions of effects together with this stability analysis will be modeled and investigated in this study to foresee does the statement is true and to foresee in what kind of condition does the hybrid nanofluid can enhance the heat transfer performance among the models. So as according to that problem statement, the main objective of this study is to model the mathematical formulation and numerically investigate and solve the boundary layer flow and the heat transfer of hybrid nanofluid for these 5 flow problems, where I will go through it one by one after this. And then this is the scope for this study, where we focus on 2D and 3D MHD hybrid nanofluid radiative flow, emphasizing on the opposing flow that is come from shrinking surface and mixed convection, and implementing the correlations suggested by Takabe and Salihi, as well as the properties by Allsop and Abunada. Then alumina and copper with water will be the main nanoparticles and the base fluid for the compositions of hybrid nanofluid. And the main method to solve the flow problem is by using numerical method, which is by BBP4C solver in MATLAB software. And these are the correlations for the thermophysical properties that will be used in the model, and these are the value for each of the properties. So now moving on to the problem 1. This is the problem on 2D steady MHD hybrid nanofluid radiative flow over a permeable shrinking surface with convective condition. So this flow problem is the extension from the problems reported by Waini et al. So here now it has been modified towards MHD radiative flow. So this is the model in the form of PDE, where we have continuity equation, momentum equation that have the MHD term, and then this is the energy equation that have the thermal radiation term, subject to these boundary conditions, where here lambda is actually the stretching or shrinking parameter, and this is for the permeable surface that with the impositions of suction or injection, and this is the convective condition at the boundary. So from that PDE, it will then transform towards this ODE by using these parameter variables. So this, the previous continuity equation will be satisfied, and this ODE is subject to these boundary conditions. So these are the dimensionless parameters that is included in this model, which is the Prandtl number, Bayes number, radiation parameter, MHD, and suction or injection. Then this is the formulations on the stability analysis, where it begins by introducing these parameter variables together with the dimensionless time variable tau here towards the unsteady versions of the PDE, and then we introduce these perturbation equations. Then finally, we will then obtain this linearized eigenvalue problem subject to these boundary conditions to solve for the stability analysis and to see whether the solutions obtained is stable or not stable. Okay, now this is the results on the effect of Cooper volume fraction towards the physical quantity of interest, where in this case, we consider the skin friction coefficient and the local Nusselt number for the physical quantities. So in this graphical result, there exists 2 solutions, which is the first and the second solution. So the increment of Cooper concentration in this case has increased the first solution for the skin friction. Meanwhile, for the second solution, there exists a conflicting point that causes a pattern to somehow completed at certain region. Meanwhile, for the local Nusselt number, the increment of Cooper concentration has reduces the local Nusselt number for the first and the second solution. And the additions of Cooper concentration also has actually delayed the boundary layer separation process as looking at the critical points. And then this is the results on the velocity and temperature profile, where the increment of Cooper concentration has increased the velocity profile for the first solution and oppositely for the second solution. Meanwhile, for the temperature profile, it has increased both the first and the second solution. Then this is the effect of thermal radiation towards the local Nusselt number. So in this case, the increment of radiation has increased the local Nusselt number for the first and the second solution, as well as for the temperature profile. Then this is the results on the stability analysis, where this is the plots for the smallest eigenvalues against the shrinking parameter that approaching towards the critical point. So from the first solution, it is seen here that it generates the positive smallest eigenvalues, which implying that the first solution is stable. Meanwhile, the second solution generates the negative smallest eigenvalues, indicating that the solution is unstable. Also, we can look at the pattern for the smallest eigenvalues, where it moves from the positive region towards zero as it approaches towards the critical point, signifying that there is decay in perturbation. So the solution is stable. Meanwhile, for the second solution, it moves from the negative value towards zero, notifying that is development or the growth of perturbation, notifying that the solution is not stable. Then moving on to problem 2, this is still on two-dimensional flow problem on unsteady MHD hybrid nanofluoridative and mixed convective flow over a movable vertical stretching surface with convective condition. So this flow problem is the extension towards the work by Isha et al., where it has been modified towards MHD radiative hybrid nanofluid flow with convective condition and suction effect. So this is the PDE that have the quantity equation, momentum equation that have the MHD term, and the mixed convection term. And this is the energy equation with thermal radiation term subject to these boundary conditions. So the same procedure is being taken in this problem as well as the previous problem 1. So we introduce these multivariables to transform the PDE towards this ODE subject to these boundary conditions. So this ODE will then be solved by using BB Posse to obtain the solutions. And then this is the formulations for the stability analysis. Actually, the same procedure is being taken as well as the previous problem. So this is the graphical results for effect of Cooper value fraction. So in this case, the additions of Cooper concentrations has reduces the skin friction coefficient for the first and the second solution, as well as for the local Nusselt number. Meanwhile, the additions of Cooper concentration in this case has quickened the boundary layer separation. And then for the velocity and temperature profile, the elevations of Cooper concentrations has reduces the velocity profile for the first solution, but oppositely happened for the second solution. Meanwhile, for the temperature profile, it has increases the temperature profile for the first and the second solution. Then moving on to the effect of radiation. So the presence or the additions of radiation towards this flow problem has actually reduces the skin friction for the first solution and oppositely for the second solution. Meanwhile, for the local Nusselt number, it has increases the first and the second solution. Also, in this case, the thermal radiation has quickened the boundary layer separation. Then for the velocity and temperature profile, the increment of radiation has reduces the velocity profile for the first solution and oppositely for the second solution. Meanwhile, for the temperature profile, it has increases both the first and the second solution. Then this is a stability analysis for problem 2, where only the first solution is stable, then the second solution is unstable. Then now for problem 3, this is on 2D steady MHD hybrid nanofluoridative and mixed convective flow over a shrinking permeable inclined plate. So this problem is inspired by the work from Alam et al. So it has been modified towards hybrid nanofluid. So this is the model in the form of PDE. We have continuity, momentum, and energy equation subject to this boundary condition. Then this is the similarity variables that used to transform the previous PDE towards this ODE. And this is the boundary conditions. And this is for the stability analysis, the formulations. So the same procedure is being taken as the previous problem. And we finally get this linearized eigenvalue problem for the stability analysis. And for the results, this is the results on the effect of Cooper valence fractions. So the increment of Cooper concentration in this case has increased the first solution for the skin friction coefficient, but oppositely for the second solution. Meanwhile, for the local Nusselt number, for the Cooper concentration on the local Nusselt number, the increment of Cooper concentration reduces the local Nusselt number for the first and the second solution. Then the increment of Cooper concentration also has delayed the boundary layer separation in this case. And then for the velocity and temperature profile, the increment of Cooper concentration has increased the velocity profile for the first solution, but oppositely for the second solution. And it has then increased the temperature profile for the first and the second solution. Then this is the results on the effect of radiation. So in this case, the increment of radiation has increased the local Nusselt number as well as for the temperature profile. And in this case also, the thermal radiation cannot be used to control the boundary layer separation process, as it will produce the same critical points. And then this is the result for the stability analysis. Only the first solution is the stable solution for practical application. Then now moving on to problem 4, this is the problem on three-dimensional flow on steady MHD hybrid nanofluoridative flow over a permeable shrinking surface with slips, viscodissipations, and Joule heating effect. So this is the study extensions towards the work by Naya et al. So it has been modified towards hybrid nanofluid flow. So we have the PDE that have the continuity, momentum equation in X and Y direction. And then we have the energy equations that consist the thermal radiation effect. This is for the term of viscodissipations, and this is the term for Joule heating effect subject to these boundary conditions. So at the boundary, we have the slip factors for the velocity slip and also the thermal slip. And then this is the symmetry variables that will be introduced to transform the PDE to ODE. And this is the boundary condition. Then this is the stability analysis formulations. The same procedure is being used here as the previous problem. So for the results, this is the results on the effect of Cooper volume fractions. So in this case, Cooper concentration, the elevations of Cooper concentrations has increased the screen friction coefficient for the first and the second solution in Y and X directions for the screen friction. Meanwhile, it has reduces the local Nusselt number or the heat transfer rate for the first and the second solution. Also, the increment of Cooper concentrations has delayed the boundary layer separations and expanding the magnitude for the critical points. And then for the velocity and temperature profile, the increment of Cooper concentrations has increased the velocity profile for the first solution, but oppositely for the second solution. Meanwhile, for the temperature profile, the increment of Cooper concentrations has reduces the temperature for the first solution, but oppositely for the second solution. And then for the effect of radiation, the increment of radiation has reduces the local Nusselt number for the first and the second solution. But however, it has increased the temperature profile for the first and the second solution, as well as thickening the thermal boundary layer. Then this is the stability analysis results, where only the first solution is stable in this case. Last but not least, this is the last problem, which is on problem 5, the problem of 3D steady MHD hybrid nanofluoridative stagnation point flow over a shrinking surface with second order slip and convective condition. So this study is the extension towards the work by Reddy and Chamka, where it has been modified towards hybrid nanofluid stagnation point flow with shrinking conditions and second order slips. So this is the PDE that have the continuity, momentum equations in X and Y directions that have the MHD term, as well as the stagnation term. And this is for the energy equation that have the radiation term subject to this boundary condition. So we consider the first and the second order slip at the velocity. Then this is the symmetry variables to transform the previous PDE towards this ODE subject to these boundary conditions. And then this is the formulations on this stability analysis to solve to check whether the solution is stable or not. Okay, then this is the results on the effect of Cooper volume fraction or Cooper concentration. So in this case, the increment of Cooper concentration has actually increases the first and the second solution of the skin friction coefficient. Meanwhile, for the local Nusselt number, it has increases the local Nusselt number for the first solution, but oppositely for the second solution. Also, it has delayed the boundary layer separation. Then for the velocity and temperature profile, the increment of Cooper concentration increased the velocity profile for the first solution, but reduces for the second solution. Meanwhile, for the temperature profile, the increment of Cooper concentration reduces the temperature profile for the first solution, but increases for the second solution. Then this is the results on the effect of radiation, where the increment of radiation has increased the local Nusselt number for the first and the second solution, as well as for the temperature profile. And in this case, the thermal radiation cannot be used to control the boundary layer separation. Then for the stability analysis, the result is still in progress. So lastly, as a conclusion, dual solutions exist, but only the first solution is verified as stable solution, while the second solution is unstable. Then the opposing flow due to the shrinking surface and the mixed convection facilitates the visibility of dual solutions. Then the critical points that describe the separation point of the boundary layer from laminar to turbulent occurs at the opposing flow region. Lastly, according to the presented findings at the opposing flow region, due to the shrinking surface or mixed convection, the heat transfer rate can be enhanced by considering lesser Cooper volume fraction, which is 1% instead of 2%. except for problem 5, and then by increasing the meridation parameter, except for problem 4. So I think that's all from me for this presentation. Thank you.
Thank you, Shah. So, any question? One question only?
One question only.
Yeah, sorry, Prof.
Okay, Shaira, so it's a question. So you have show your result as in the graphs. Only that I just wonder, okay, you have that there are you have two solutions, first
Yes.
solution, second solutions. Well, I just wonder, do you think that it might exist a third solution? How do you know that there's no third solution and fourth solution? That means for your model, the result there's only first and second.
Okay, it is actually possible to have a third or fourth solution and more, depending on the initial guesses that I set at the BVP4C coding. So for this case, I only set for 2 different initial guesses. So I expect to have 2 different solutions.
I see. And so far I know that for you to guess, for you to choose the suitable guess, it also take times, right?
Yes.
Yeah, so that's why that means it's possible to have the third solution or fourth. Okay.
Yeah.
And then, well, from your presentation, I can see that your first solution is always stable compared to the second solution.
Yeah.
Is there any reason why? Or the fifth problem you haven't tested yet, but the first 4 problems, all the second solution is not stable. Do you think there's any reason?
Basically, we will always expect for the first solution to be the stable one. So if even we get either one of the solution is unstable, so we always expect for the stable solution to be the first solution.
Okay, I just wonder because you claim that you obtain the first solution is from the initial guess, right? That means different initial guess, you will get different solution. So I just wonder, that means there must be something unique in the initial guess that you choose. And that initial guess, you obtain the first solution, and that's the stable point compared to your second initial guess, and you get the second solution, but that is not stable. I think it's something interesting for we to study about it. Something unique in it.
Boleh saya tambah sikit je?
Yeah. Dr. Nick.
Syaira,
Yes.
It seems that untuk tentukan the stability of the solution that yang awak dah buat, you do it secara numerical, right? Semua yang awak buat tu secara numerical daripada differential system of differential equation or reduce gunakan similarity variable transform to linear eigenvalue and so on and so forth, and then you dapatkan those things. So untuk menjawab soalan Prof tadi, so I would but this is not the norm of the way you guys doing it. It's good kalau awak boleh dapatkan, awak boleh buat ataupun dapatkan condition, a certain condition that need to satisfy so that your solution is stable. So maknanya bila kita lakukan proses itu, kalau condition itu dipenuhi, satisfied, so the solution is stable, so that you can choose whatever initial guess. As long as it satisfies those conditions, then inshallah it's stable. So that's the answer, easy to answer, but I believe this is the norm of research that you do. Thank you. That's just my suggestion.
Okay.
Thank you.
Okay, thank you. That's all.
Okay, thank you.
Thank you, Prof. Zanaria and
Dr. Nadiha, satu komen saya.
Oh, komen. Oh, boleh sikit.
Syaira, saya tengok simbol yang kamu guna.
Saya tak finalize.
Sebab ada yang kamu guna lambda untuk shrinking, ada yang kamu guna lambda untuk mix. So, minta selaraskan ya.
Okay.
Sebab ini kamu akan buat tesis dengan sama, simbol yang sama.
Okay.
Alright, thank you, Dr. Nafifah, for the comments. And can we go back to the Muhammad Al-Amin? Are you still here? Let me see.
Yeah, I'm still here.
All right.
You hear me now, Doctor?
Yeah, you can try to share.
Yeah, okay.
Yeah.
Still there's a problem. I don't know what's the problem.
Go to the share screen. Yes. Okay. All right. You can see that.
I cannot see the presentation.
We can
I
see
don't know.
your screen, the whole screen.
Yeah, but the result that I need to share it does not exist. Don't know why. The file.
Did you open the window?
Yeah, I opened the window.
You have to open your slide first.
Yeah, I opened it first.
And then share screen.
Yes, you open your slide first, then you share screen.
Okay, wait a minute, okay? Do I need to go and join again and then share? Oh, and now I open it.
This is latex file.
Yes, latex file. You can see now?
Yeah. How about supervisor? Is it okay? So
you see the,
this is not your slide. This is your latex file.
Yeah, just 1 minute.
Do you have the PDF?
Yeah, I have the PDF, but I don't know what the problem exactly.
Try to run, and I think we try to run and then produce the PDF file, and then we can see.
Okay, let me see. La ilaha illallah. Astaghfirullah al-azim.
Yeah, I think you can try to figure that again.
I don't know. I think it's a problem like today. I'm very sorry, really.
Try to run again and then produce the PDF file.
Okay. Now let me. You can share.
All right.
I sorry for that. Just let me try. Astaghfirullah al-azim.
Okay. Try that again, and I think.
Yeah.
You can. We can go back to the next presentation.
Just give me 1 minute, 1 second. Give me 1 second. Let me see now. It's open on that. 1 second, please.
All right.
Satu second ini 20 second ini.
You can go. Let me try it. Okay. You can choose another.
Okay. So we can go to the next presenter.
Okay. Good.
Maybe we can go last for you. Okay.
I will stay. I will keep stay. Sorry for that, Doctor. I'm very sorry.
All right. So the next presenter is Al-Sa'di Al-Kawthar. Kawthar?
Yes, I'm with you.
All right.
I will share my slide.
Yeah, sure. All right. Just a reminder that you have 15 minutes and 5 minutes question and answer. Okay, you may proceed.
Just 1 minute. I want to see this. Okay. Bismillahirrahmanirrahim. My topic, theoretical study for some classes of fraction integral differential equations in Banach space with numerical analysis under supervisor Prof. Nick and committee Ibrahimov and Prof. Nur Razak and Prof. Senetin. The outline of my presentation, introduction and literature review, problem statement, and objective primarily, and results, and stay for class 1 and class 2, class 3 for my results, equations, and then conclusion. For introduction, fractional calculus branch that studied and extended of the differential and integral equation and operators from integer order to fractional order, which used to interpret the natural phenomena. Fractional integral differential equation is one branch of this fractional calculus that has more attention and interest for modeling different problems. For studying this mathematical modeling in terms of classes of integral differential equation with fractional order gives a suitable and accurate.
Your voice is not clear, Kausar. Kausar?
Yeah.
Kausar?
I'm hearing.
Your voice is not clear.
I'm trying.
Please make it your clear.
Okay. Okay. Studying mathematical modeling in terms of some classes, in terms of fractional integral differential equation with a fractional order, gives suitable and accurate interpretation and approximation solution for some natural phenomena in different fields. For literature review, we have this equation, Volterra-Friton integral differential equations, equation 1 and equation 2. And for these equations, we have a researcher in 1 and 3 used some fixed point theorem to prove the existence and uniqueness of solution of fractional integral differential equation in the first equation. Also using several operators, Caboto and Hilbers and Hadamard and conformable operators. Other also interested to analyze the stability of the solution. Also other interested to approximate solution by using different numerical approach like homotopy perturbation and reproducing kernel method and residual power series method and atomic decomposition method and also Laplace decomposition method. For problem statement, there's a lack of studies have been done in literature dealing with some class fraction integral differential equation benefit space and then some operators of Caboto derivative of mixed fraction differential equation and Caboto conformable and field Caboto fractional integral differential equation, studying them theoretically and numerically. Studying these classes comes to adding some new damaging literature as adding a new proof existing equation or represented sometimes a fractional differential equation or constructed some new classes with different initial or boundary conditions. The objective of this study to investigate the existence and uniqueness of the solution of Caboto conformable and phi Caboto fractional integral differential equation using different fixed point theorem to introduce a new class of Caboto conformable fractional with the 3 non-local Riemann level conformable integral, introduce a new class of phi Caboto derivative higher order with initial boundary condition and apply the new generalized Grunwald inequality in sense of Riemann level conformable integral and employing some inequalities as the Grunwald inequality, Grunwald with Caboto.
Also, I think something wrong with your mic. It's not really not clear.
I'm trying, I don't know why. Okay, this okay now? It's okay now?
Yeah, try, go on.
To employing some inequalities with Grunwald inequality, generalize Grunwald inequality with Caboto inequality and phi Caboto and Riemann level conformable integral with theoretical aspects to prove the analyzed stability of the solution using definition of uniform stability and Ulam-Hare stability and dependence continuous with order parameter, change order parameter. Also to approximate solution given in class using different numerical approach, Laplace Adomian, DGJ and Adomian and ADM, operational derivative matrix of Bernstein polynomial with a U constructed to analyze the convergence and to derive the maximum absolute error for some suggested method, and also to demonstrate the efficiency of our method based on some numerical results with supported example in the theoretical part and numerical part. We need some preliminary definition and theorems. We need Riemann level fractional integral and Caboto fractional derivative. Also, we need Riemann level conformable integral equation 3. Also need Caboto conformable derivative equation 4. Also phi Riemann level fractional integral and phi Riemann level fractional derivative in this equation. Also, we need some Laplace transform Caboto derivative equation 5 and Grunwald-Pillman's inequality. And we need Grunwald lemmas with respect to phi function, to psi function. And some fixed point theorem like Banach fixed point theorem and Scavar fixed point theorem and Arzela-Ascoli theorem and Arskovsky fixed point theorem. Move to my results. We start with the first class. The first class Koboto fractional mixed Volterra-Friedholm integrated differential equation with two initial conditions. This class in equation 6 with initial condition W0 equal W0 and W prime 0 equal W1. And for this equation, we suggested some axioms depend on satisfy the Lipschitz conditions and the boundedness condition from A1 to A3. And for these conditions, we convert the integral equation to integral form, as we see in this lemma between alpha between 1 and 2. And for this omega, we define the operator in this lemma called omega in equation 7. After that, we have two lemmas, lemma 1 and lemma 2 for omega to prove if the omega satisfy equation, satisfy the condition A1 and A2 and A3, and also want here in lemma 1 and 2 to prove its completely continuous operator and its bounded set in Banach space. For this proof, we prove theorem the existence of the solution depends on the previous lemmas using the Scavar fixed point theorem and satisfy the axioms A1 to A3 and the omega operator defined in equation 7. Then the equation has at least one solution on the interval. For uniques of the solution, must satisfy R less than 1 and satisfy the three conditions, then the equation has a unique solution on Banach space. For stability, if the equation satisfy if the inequality in equation 8 satisfy the condition from A1 to A3, and if there exists xi greater than 0 or epsilon greater than 0, then there exists the omega W as a unique solution satisfy the equation 9. Then the equation is stable. This Olam stable. For this definition, we prove the theorem Olam higher stable with xi, choose xi in this form greater than 0. Then the equation is Olam higher stable. For the approximation method, we use this Laplace domain decomposition method. We applied Laplace for both sides on the equation, and then take the solution in the infinite series in equation 12 and equation 13 and use equation 14. And then find take Laplace inverse. We have equation 19 and equation 20. And for this, we have this equation example. The example 1 from the literature, solve this with n equal 10 in different values of alpha. And we have this result. And the results converge to the exact solution at alpha equal 2. And we have this figure. Also for literature, we have at alpha equal 1.5 compare the result with Adonian decomposition method and homotopy method, analysis method, and we see this in alpha equal 2. That's more difference between the Laplace Adonian and homotopy. That the result state that the Laplace Adonian decomposition method is very accurate, gives accurate result exact solution with the absolute error 10 minus 16. Example 2 also computed at n equals 6. And then this is the result. And for example 3, with the linear part, we have and n equal 10, this result. Okay. The second class was coboto-conformable fractional Volterra-Friedholm integral differential equations with non-local Riemann level conformable integral boundary condition. The equation in 23. And for this equation, we have this, we define this constant. And for this constant, we convert the equation to integral form in equation 25. After that, we generalize Gromov inequality in sense of Riemann conformable integral in equation 26. If absolute chi satisfy this equation, then there exists L greater than 0 L star, such that chi u absolute chi u is than or equal L star. Converted this equation to operator omega in equation 25 and 27, and then we prove the existence and uniqueness by suggested this hypothesis H1, which defined Lipschitz conditions on the function, and use this to prove the uniqueness of the problem, such that Q less than equal or less than 1, then it has a unique solution. And the hypothesis H2 about boundedness, if this satisfies and holds, then the equation has at least one solution, and this was proved by scalar fixed point theorem by 4 step. And then studying stability by define chi bar in this form in equation 30, and then define the uniform stability. The solution is uniform stability if there exists psi epsilon greater than 0 satisfy this equation, then chi lu minus chi bar less than epsilon. For this definition, we proved the theorem uniform stability if at 1 and condition Q1 less than 1, then the solution is uniformly stable. And we use the DGGIM technique to solve it approximately by use chi u in equation 32 and substitute the series solution chi u equal summation chi m in 33 and substitute in 32. Then we have this algorithm, and for this algorithm we applying some example. Before that, we prove the convergence for this method by this theorem, and we find where the absolute error chi y minus chi n less than r1 plus r and r2 to power n chi naught, such that r1 plus r2 less than 1, and the series solution conversion to exact solution if satisfy this condition in this theorem. And we use ADM decomposition method also to solve this equation. And this is algorithm. For these two methods, we have this example. The first example and the second example about the theoretical part. In this example, we prove this equation has if Q less than 1, then have this unique solution. Okay. And for example 2, it has at least one solution in this by applying the condition. For example 3 and 4 is numerical part. The table here for mu equal 0.9 and theta equal 1.5, and we have ADM and DGM. This is near for each other in this example, and this graph showed that. For example 4, it's more accurate because here we find this that's Adonian, that's DGIM is better approximation than ADM and nearest and close to the exact solution as we see here in this graph. The last classes was the new Algebra-Fruithome fraction to differential equations. They have fixed proposal derivative high order with initial boundary condition, and this is in equation 43, such that phi is increasing differentiable function, satisfy p prime not equal to 0 for all u in C node and C, and we convert it to integral form in equation 44, and then we suggested these two hypotheses H1 and H2 for boundedness and Lipschitz condition. And for these conditions, we define omega operator in 45. This operator, we use it to prove the existence of the solution if H1 holds, and then the phi-copoto fraction of Volterra has at least one solution, such that satisfy this NR is the compact set, satisfy X, and the norm of X less than R greater than 0, and also divide psi1 and psi1 and psi2 in equation 46 and 47, and complete the proof in step 1 and step 2 and step 3. The last theorem, uniqueness, if H2 holds, then phi-copoto fraction has a unique solution, and this applying Gromov inequality phi-copoto trigonometry. And for stability, if this condition satisfies less than 1 and H1 and H2 holds, then this equation have satisfy the stability such that X epsilon naught minus X is in order of epsilon, where epsilon is sufficiently small. For numerical part, we suggest operational derivative matrix Bernstein polynomial, and this is still under work. This is my conclusion. Some of these new classes need to study, and we continue and progress this work. Thank you.
All right, thank you, Kauthar.
Thank you.
Questions from supervisor or evaluators?
For problem number 3 or class 3, have you proved all the theoretical parts?
Yeah, I prove all theoretical parts,
including the stability.
Including the stability. All 3 parts are finished. They're finished.
All right. Okay. So for the numerical, so you suggest operational metric derivative matrix or Bernstein polynomial. I see. So
yeah.
you use the polynomial approximation using polynomial.
Yeah, but here not the normal Bernstein. We constructed a new Bernstein polynomial with respect to the kind of my equation.
I think if you use polynomial, you might need again to prove the convergence as well.
Yeah. There's another part for theoretical, depends on this method.
All right. Okay.
Yeah.
All right. Thank you, Ratani, and also Kauthar.
Thank you.
I would like to call upon the next presenter.
Now can I present?
Divika.
Yeah, hi. Assalamu alaikum, Doctor.
Can you do it right now?
Yeah, I'll try. Doctor, you hear me, Doctor?
Yeah.
Okay, I'll try to share now, inshallah.
All right.
Yeah, you can see my slide
yes,
now?
You can see.
Okay, inshallah, alhamdulillah. Sorry for making this delay.
So you have 15 minutes and 5 minutes for question and answer.
Okay.
Begin right now.
Okay. Now this is not presented now. Just 1 minute. Okay, my name is Muhammad Al-Amin Abdullah. My presentation is titled is that utilization of pure model with generalized modified Wabi exponential distribution for analysis of cancer patient. My supervisor, Dr. Muhammad Shafi, I'm of Dr. Habshamidi, and this is outline of my presentation. When analyzing time to event data, it is often happened that a certain fraction of data when they experience the event of interest. This is so you call that is being pure, and the time will be infinite. Survival models that take this feature into account is called a pure model. In the literature, there is 2 types of mixture of model, mixture pure model and non-mixture pure model. Equation 1 represents a mixture pure model. And the equation 2 represents bounded other cumulative function. And equation 3 and 4, we utilize them together to get equation 5. And this, when equation 5 have geometric non-mixture pure model, and equation 6 represents the density function of this model. Here in this stage, we use 2 distribution, generalized modified Wabi distribution, which is represented by equation 7, and equation 8 represents it is a survival function. And then this model, we have 8 sub distribution. We call that some special distribution. for different values of alpha and beta. And the second distribution we use here, y with exponential distribution, equation 9 represented is density function, and equation 10 represented is survival function. And the distribution from 1 to 5 represents some special cases from Weibull distribution. And then our problem statement, we know that the Weibull distribution is the one of the distribution widely used in the cancer research due to its flexibility of decider and easy to estimate this parameter. However, Weibull distribution not provide a good fit for phenomena with non-monotone failure rate like past shape and mononomial. Such data require more sophisticated model to present it. So in this case, we we have to use some type of modeling values that is big extension of Weibull distribution, like log likelihood, and then the other one like generalized modified Weibull distribution. Moreover, there is another situation in the cancer research that some subjects are not experience the event of surrogate. In this case, the population is divided into two parts, like cured and uncured. And the research objective of this study was to extend the parametric cure models and non-parametric cure model to incorporate right sensor data and the fixed covariance, also to extend and modify the mixture cure model to be an alternative to mixture cure model bound comparative hazard model, and to incorporate right and interval sensor data. And they said that we use two distribution, geometric circular and the generalized modified Weibull distribution. Also to propose a parameter estimation technique for the following cure models to evaluate the performance of model by simulation, to compare between mixed cure model based on exponential, Weibull exponential, sorry, by using simulation. Also to illustrate the application of developed cure model using two different data from cancer research, namely melanoma and leukemia. This is my main references that I use in the literature. Now I come to the methodology. I'm using maximum likelihood estimation, and then equation 11 represent log likelihood estimation for mixed cure model, and equation 12 showing that the log likelihood function for this model. Equation 13 for the maximum likelihood for bounded comparative hazard model, and equation 14 it is log likelihood for bounded comparative hazard model. Here in this case, we study the interval sensor data. In the case of bounded comparative hazard model, equation 15 is showing that the log likelihood function for this model. And we know that when you have the time will be interval, that the time cannot be observed, it's only observed in an interval. And then we have the log likelihood for this one for equation 15. And then this model can be further extended to the left and interval array sensor data. And we can use this indicator, delta Lj, delta I, and delta Rj. Then you can get the likelihood function for M interval sensor data. Equation 17, we're showing the likelihood function for this. Then now when we use the generalized modified Weibull to replace it to get the log likelihood function for bounded comparative hazard method, this can be given by equation 18. And now we go to the simulation. The first part of the simulation, we use the mixture cure method based on generalized modified Weibull distribution. We base our replicate in one size, the replicant 50 and 100, 230 sample size, and we use one setting covariance with two different scenarios, one for Bernoulli 0.5 and the other for uniform 0.01. And then the right sensor data we use from Rambus 2020, and the steps are follows. And then we get these steps from this data, and then we are considering the bias and the standard error and root mean square. And as we know that the values of the bias and the standard error and root mean square, if they are small, they indicate that the good responsibility efficiency of estimate. And then table 1 is showing that the biases are very small, and the standard error and root mean square decrease when the sample size is increased. And in the two scenarios that we have, the simulation study showed similar satisfactory result. And now we go to the bounded comparative hazard method. We use under the right sensor data and interval sensor data, and then we get the steps for doing the simulation. And these are the steps that we followed, and then we get the result in table 2. The average estimates are very close to the respective parameter, and the values in different settings of sensor. As the estimate are all examined values for the moderate censoring rates and heavy censoring, because we use the moderate censoring here for 32%, and for the heavy censoring 67%. And in the moderate censoring is better than the heavy censoring that we calculated. And then for interval sensitive data, we have one covariant and we have two scenarios. And then we fix the time between two examined interval, which is B0.5. We keep it as a constant. In the second scenario, we assume that the links of the center can be drawn from the uniform 0.2 and 0.7. And we follow the same seminar for simulation in part A. And for interval sensor data, we followed Ban and Kim in 2018. And these are the steps for getting the result for this model. And then table 3 showing that the bias are very small, standard error and root mean square decreases when the sample size increases. And for the both scenario, we can see that simulation study shows similar satisfactory result. And then for non-geometric mixed circuit model, we follow the same, but we follow the different scenario for the simulation. We go following Rambus 2020. And then we can get the result for this. We have 20% for middle, and we have 41% for fixed covariance. And for the following different scenarios, these results illustrate that the bias are very small, and the symmetrical origin diameter perform for high sensory rates than better censoring. Here we have 22 for the moderate, and we have 41 for the moderate. And then we start with geometric dynamics and miracle model based on exponential viable exponential. We have sitting here of three covariants, x1, x2, x3, Bernoulli, and uniform. And then we use two different scenarios here for censoring, 22 and 41. And we use the same simulation in part A3. And then we have here results for the two different scenario rates. The bias estimate are very small, and the estimate of all parameters are better in the light censoring based on the moderate censoring. Okay, and now we came to our application for the real data. Now we use leukemia data. This consists of 91 patients, 46 patients exposed to allogenic, and the second group 45 received autologous. And then we found that we have 24% of right sensor data, and the event it is time to test. Now this is the Kaplan-Meier, which indicate that there is a cure fraction in the two group allogenic and autologous, and these indicate that the cure model is appropriate for analyzing this data. And now we use the maximum likelihood for mixture cure model, and we found that the generalized modified Wabner exponential provide small values of AIC, and we know that the small values of AIC indicate better fit. Now, in this figure 2, again, we have another group that generalized modified Weibull and exponential. They provide this better fit to the leukemia data, and this provide the closest anticipate values from empirical, and it is very clear that from the graph. And now here, in this figure, we have the survival function and we have the Hauser function for the same distribution G. And then we see that in bundle B that we can find that the generalized modified and exponential, they have produced that the very, very closer to Kaplan-Meier. And in bundle D that we have the corresponding hazard function for these two distribution are closer to each other, the red one and the blue one. And this means that they are given the closest to each other, and it proves that they are the better distribution for fitting this data. And now for this one, we put the generalized diaphragm function with the covariance, and we have B naught and we have rho naught and rho 1, which is the cure rate for allogenic, and rho 1 for the cure rate for autologous. And when we study the ratio between rho naught and rho 1, we find that it is 1 point something, which is and the 95% confidence interval for this value, it is not included one, indicating that there is a proof of difference between the population cure rates. And now we go to the second data, which is the Millionaire data, which is 2-arm clinical trial that we have high dose and we have interference and with control. And here we have 96% of patients experience the cancer, and the remaining are right sensor. And we have kind of more information about this from 1996. And here is the Kaplan-Meier for this data. Back again, we can see that the cure model can be suitable model to analyze this data. Here we make a comparison between mixer cure model and boundary combination hazard model and the geometric model, 3 of them. And we find that based on exponential distribution based on for these three models, we found that they obtain the same result. This means that they are equally fitting the data, but there is slightly different when we look at the mixture cure model based on exponential wide distribution. And this means that the mixture cure model based on exponential wide distribution is better than bound combinatorial hazard method and geometric mixture method, both of them based on the exponential viable exponential. And here we can see from this graph that exponential viable exponential show that the better fit when we use it with the mixture cure model, other than the other, better than the other cure models. And now we here in this table, we fit the three models together with the include the covariant, and we see that the value of AIC, BIC, HIQC for all three models almost the same, but again, the mixture cure model showing the better result as we prove. And in this figure, we have the survival function and hazard function obtained from this one using exponentiated viable exponential distribution. And now here we come to our discussion evaluation of the estimation of particular parameters. Simulation study indicate that the proposed method yield estimated coefficients that are very close to their respective true value. And the good performance of the proposed method was evidenced by values of by standard error and root mean square, and it was apparent that the level of censoring decreased. The simulation result says that overall performance of maximum likelihood estimate for the given methods were appreciably good, and regardless of the sample size and censoring rate. And our conclusion, in practice, the use of cure models should be based on satisfactory empirical evidence of the presence of cure fraction. This means that it is have to check that there is the presence of cure, and then large sample size and small censoring proportion and long-term follow-up to be a very important factor for improving the efficiency of likelihood estimate. For the leukemia data, we found that exponential viable exponential and generalized modified viable distribution are the best choices of survival times compared with other distribution. And also, we see that Cox proportion hazard proportion is not appropriate for this analyzing data. Why? Because when we check the hazard function, we find the hazard function of this one that are overlapping, and this cannot be used for the Cox proportional hazard. So this means that the cure models are better. For mononomial data, exponentiated viable exponential distribution is the best distribution for the survival times of susceptible patient compared with EEE, which is exponentiated viable, and exponentiated Rayleigh exponential, and exponential, and viable exponential, and Rayleigh exponential distribution. The important point that we have that the geometric mixture cure model can be considered as the good candidate for this model, because already when we compare the three models together, we found that all of them, they show the same result, but the maximum likelihood, I mean, when we case for the mixture cure model is slightly high, but this means that the geometric mixture model can be considered as a good candidate. And here, this is my publication. We have two articles. The first one is cited twice times. The second one is cited one times. Recently, I'm doing the third article. It's in progress to submit under the title Analysis of Lung Cancer Data employing a mixture cure model with the generalized exponential distribution. And this is my references. And thank you very much for following me. And I do apologize for the technical issues that happened at the beginning of this presentation. Hello?
Yes, thank you,
Yeah.
Muhammad. And also that is quite fast.
Yeah.
All right. So any question from evaluators or supervisor?
Yeah, Dr. Nadiha, Dr. J here. Can I just make a quick comment?
Yeah, sure.
Okay, Elamin, looks good. Looks like you took in all my advice the last time.
Yes, yes, I use it. Yes, yes,
yeah,
yes.
Good.
You're right.
Just one comment.
Yes, tell me.
I noticed that you use wall for the confidence interval estimate, right?
Come again?
The confidence interval for the real data, when you did the application, you used the wall confidence interval, right?
Yeah, I use 95%.
Yeah.
Yes.
Why don't you add another component in your research where you do you compare several inferential procedures for your model? Because this is new.
Yeah.
Probably wall is not the best at all sample sizes. So maybe some of the, you could look at other confidence interval estimation methods to see which performs the best. Maybe you can look at bootstrap, you can look at likelihood ratio instead of just wall, because wall sometimes fails when the sample size is small. It's just an idea. Because what do you plan to do for your future work?
Yeah, for my future work, I'm starting, as I said, doing here. Recently I'm doing this third article.
Yeah, maybe I missed it. Can I just have a look?
Yeah, let me just show you the, sorry, let me show you the slide, that one. I'm working on that.
Yeah.
Just 1 minute.
It's okay, take your time.
That's okay, no problem. Yeah, here it is. Analysis of lung cancer data employing an unmixed pure model with generalized exponential distribution.
So because you're doing all mostly is models, application parameter estimates, right? It will be
Yes.
really good if you have inferential procedures, because
Good.
then when you publish a paper, you can show the estimation part and the interval estimation component, the inferential part. I mean, it's just an idea because
No. Yeah.
yeah.
Tell me, sir. Yeah,
Yeah,
I
I think it will be a good addition to your PhD.
I will.
Yeah,
I will
and
do.
it's easy. I mean, it's easy. You just have to compare Wald with
Okay.
probably, you can pick up anything, Bootstrap or just another confidence interval. See which one works the best.
Okay.
And that can be like one topic in your PhD.
Okay, that's good. So now I can making the comparison between Wald and Bootstrap.
Bootstrap or likelihood ratio, you can look at likelihood ratio, you can look at jackknife. There are a lot of confidence interval estimation methods now. And you know, these computational methods, they sell now because they are journal which just focus on computer intensive techniques. So you can send your paper there.
That's good. That is,
okay, that's all. It's just a comment.
No, it is a good comment, because all the time I'm ready to listen to you and to get your advice. This is what I develop my work. So I'd be very happy.
And I'm very happy with your work. I mean, this time.
Quite happy. Thank you. Thank you very much. Thank you very much.
Okay.
Yeah. So if you don't mind, if you don't mind, Prof, I will send you the suggestion for the shared article.
Of course.
And you can share. Thank you, because it's a good idea. Thank you very much, and God bless you. Thank you very much.
Thank you, Dr. Nadiha.
Thank you very much.
All right. Thank you, Dr. J, for advice, and also Woman Alamin for your presentation.
Yes. Thank you very much.
You may. All right. So next presenter is Divika.
Hello, Doctor.
Yes.
Okay, so I will start sharing my screen.
Yes. You can start share, and then you can begin any moment.
Okay, so I hope you can view my screen.
Yes.
Right?
Yes.
Okay.
Can you just control? Yeah, full screen.
Okay, so I will just start. Okay, a very good morning to my supervisor, Dr. Ida Marif Ajalias, my co-supervisor, Dr. Gafurjan Ibrahimo, Dr. Isman Mahashim, all the respected lecturers and fellow presenters. My name is Divika Nai, daughter of Madhavan, and the field of my study is in differential game theory. The topic that I'm going to present today is differential game problem described by an infinite first-order tree systems of differential equation in Hilbert space L2. Okay, so let's get started. Okay, what is differential game? So differential game theory is basically a theory that is used to study the player's strategy in order for them to achieve their respective objective, where the motion of the players are defined by some differential equation. Okay, so in differential game, the pursuer's motive is to catch the evader for some time on a finite time interval to guarantee the completion of pursuit to take place in the game. Whereas the evaders aim to avoid from being captured by the pursuer to ensure the evasion is possible either on a finite time interval or indefinitely. Okay, so in most of the differential game, the control function of the players are subjected to either geometric constraint, which limit the speed of the players, or integral constraint, which limit the total resources of the players. Okay, the constructor strategy for the player is said to be admissible if they satisfy either geometric constraint or integral constraint. Okay, so when we are dealing with pursuit differential game, the pursuer will move in accordance to the admissible constructed strategy, whereas the evader is free to move. Okay, so the statement over here will be vice versa when we are dealing with evasion problem. Okay, so the game takes place in Hilbert space L2, which has infinitely many components with the following inner product and norm. Okay, problem statement. In this study, the existence and uniqueness of solution of an infinite first-order tree systems of differential equation defined by 1.1 here is being investigated. Okay, so there are three games that are being studied. Okay, we have game one, where the pursuer's motive is to bring the initial state of the system into zero state on a finite time interval, whereas the evader prevents it from happening. Both integral constraint and geometric constraint are considered on the player's control function. And then we have game 2, where the pursuer wants to bring the initial state of system into another state defined by mu1 on a finite time interval. Integral constraints are imposed on the player's control function. So in both game 1 and game 2, sufficient conditions to solve the control problem as well as pursuit problem are investigated. Okay, and then we have game 3, which is an optimal pursuit differential game with integral constraint constraining the player's control function. Okay, so here optimal strategy for the players are developed and optimal pursuit time is figured out. Okay, so for objective, it's basically to find and to prove the existence and uniqueness of the solution of infinite first order tree systems of differential equation. Okay, after that, to solve the pursuit problem in both game 1 and game 2 in accordance to the pursuer's motive. And then in game 3 to solve the optimal pursuit differential game. Okay, for the scope, the equation of the game is an infinite first order tree systems of differential equation, and the game takes place in Hilbert space L2. Okay, literature review. The study of this differential game theory was started by Rufus Isaac in 1965, and it mainly deals in the investigation of pursuit problem, evasion problem, or both pursuit evasion problem. Okay, so in the early part of the study, there were many investigations have been carried out where the equation of the games are defined by partial differential equation. So in order to simplify the solving process, the researcher used method of decomposition to reduce the system into the one described by an infinite systems of ordinary differential equation. So here are some of the works that have demonstrated the method of decomposition. Okay, so following this, many attempts that have been carried out to explore differential game problem defined by infinite systems of ordinary differential equation. Okay, and in most of the pursuit differential game, the pursuit is said to be completed if the initial state of the system reach origin at a finite time. So listed here are some of the examples of work. Okay, for instance, we can see in 2017, Ibrahimov et al. Explore a differential game defined by first order two systems of differential equation in the space of L2 with geometric constraint constraining the player's control function. Okay, so they solved the control problem and they constructed an admissible strategy for the pursuer to obtain the guaranteed pursuit time. Okay, so besides that, some of the works were interested in studying the optimal pursuit time of the differential game, as can be seen here. Okay, so in order to obtain the optimal pursuit time of the differential game, they have constructed optimal strategy for the players. Okay, then for this one, in contrast to the previous work, there were some studies have been done to study the completion of pursuit where when the pursuit brings the initial state of the system into another state on a finite time interval. So all these are the examples. Okay, so in our research, we have designed an infinite first order tree systems of differential equation, and we have explored two cases of pursuit problem and optimal pursuit time of the differential game. Right, so methodology. As mentioned earlier, our focus here is to study differential game problems defined by an infinite first order tree systems of differential equation, where mu t represent the solution of the system. Okay, so this is the form of the control function of the players when they are subjected to either geometric constraint or integral constraint. Sorry. So first and foremost, we solve the system and we prove its existence and uniqueness. Okay, so this definition is related to the solution of the system. So note that every step written here is followed with its related definition. All right, so the next one is to investigate the control problem of the system to obtain an admissible control function that can stir the system into origin in game 1 and game 3 and into another state mu1 in game 2 on a finite time interval. Okay, after that, we are going to construct an admissible strategy for the pursuer so that this admissible strategy can be used to complete the pursuit in the game. Okay, so the next two steps take place in game 3 where we develop an admissible strategy for the evader to obtain optimal pursuit time for the differential game. Okay, so based on definition 3.10 here, the time theta bar indicates optimal pursuit time of the differential game if it is the fastest time the pursuer can take to complete the pursuit, and the evader can only sustain evasion for all time before time theta bar. Okay, so here comes the main result. So we obtain the solution of the system mu t in the form of 4.1, where you can see phi kt here represent the fundamental matrix of the solution. Okay, and this fundamental matrix exhibits 5 main properties that we are going to use in the succeeding proof. Okay, Theorem 4.1 here claimed that the solution of the system belongs to space of continuous function on time interval 0 t in the space of L2. Okay, so we divided the proof into two parts. In the first part, we want to show that the norm of the solution of the system is finite to indicate the solution of the system belongs in Hilbert space L2. Okay, so to get from here to here, we utilize property 4 of the fundamental matrix just now, and for this part, we utilize Cauchy-Squarch inequality. Okay, and then in the end, we get that the solution of the system is in the space of L2. Okay, in the second part, we want to prove the solution of the system is a continuous function on time interval 0 t by employing epsilon delta approach. So the proof is as follows. Okay, it's a very long proof, but then in the end, we get that for every positive epsilon, we may choose positive delta such that this norm of this term will be less than epsilon, which proves the continuity of the solution. So this completes the proof. Okay, so now we are in game 1, where the pursuer's motive is to transfer the initial state of system into 0 state on a finite time interval. Okay, in the first case, we consider integral constraint on the player's control function. Okay, so we deal with the control problem. Okay, so here we have equation var pi kt given by 5.2 together with its inverse given by 5.3. Okay, so in the construction of theorem 5.1 here, we are required to develop the condition 5.4. Okay, so first of all, we develop control function wt given by 5.5 and we prove its admissibility. Okay, so note that this term here is actually a vector, so we are required to find the norm square of this vector in the proof as shown here. Okay, so observe that this last line here is actually equivalent to the summation of this one. So this means equation 5.4 just now is satisfied. So it indicates that the control function wt satisfies integral constraint. Okay, after that, we use this admissible control function to shift the system into origin at finite time t. Okay, next we proceed in examining the pursuit differential game, which includes pursuer's strategy. Okay, so here we claim that the guaranteed pursuit time t, capital T, obeys equation 5.7. Okay, so in order to prove theorem 5.2 here, we develop strategy for the pursuer given by 5.8 and we prove its admissibility. Okay, and then after that, we prove that the pursuer can use the constructor strategy to terminate the game at finite time t. Okay, so next, geometric constraints are imposed on the player's control function. Okay, so for here, we carry out similar pattern of investigation, but this time with respect to geometric constraint on the player's control function, in which we perform steps to obtain admissible control function in the control problem and an admissible pursuit strategy in pursuit problem to bring the initial state of the system into origin at finite time. Okay. So next is game 2. Here, the pursuer wants to shift the initial state of the system into another state mu1 on a finite time interval. Okay, so we have control problem in which the time t is set to obey equation 6.1, and you can see the equation 6.1 here holds information on initial state of the system as well as another state of the system mu1. Okay, so to prove theorem 6.1 here, we develop an admissible control function wt. Okay, so notice that for this line, we perform the following calculation until we arrive here. Thus, by substituting all the obtained information, we get that the control function wt satisfies integral constraint. Okay, and then we prove that this admissible control function can shift the system into another state mu1 at finite time t. Okay, so by referring to the solution of control problem just now, we proceed in studying the pursuit differential game. So here we construct an admissible strategy for the pursuer to terminate the game at finite time t as soon as the system reach state mu1. Okay, so moving on to game 3. So here our focus is to study the optimal pursuit time of the differential game. So first of all, we examine the control problem. In the first part, we construct a control function satisfying integral constraint that can steer the system into the origin at finite time theta. And then in the second part, we want to prove that the system cannot be stirred into origin for all time before time theta by the means of proof by contradiction. So here's the proof. Okay, so here we have proposition 1, which we use to construct the potential admissible control function. Okay, so according to the proposition 1 just now, the constructed control function should give minimum value to this one. However, we notice that the control function WT fails to be admissible. So this contradicts our hypothesis, which means assumption made is wrong. Therefore, if there exists an admissible control function, W, then the equation is possible to take place in the game for all time before time theta. Okay, so moving on to differential game problem, where here we want to prove time theta bar is the optimal pursuit time of the differential game. Okay, so we introduce lemma 7.2 to assist us in the proving process. Okay, so in the first part, we prove that the pursuit is possible to take place at finite time theta bar by constructing an admissible strategy for the pursuit. And then in the second part, we prove that pursuit is impossible to take place for all time before time theta bar, Okay, so here we have lemma 7.3, which discusses about the amount of energy left for the players. Okay, so here we construct an admissible strategy for the evader. Okay, again, we prove by the means of contradiction. So the proof is as follows. Okay, so you can notice here, we utilize the proposition 1 as stated earlier. Okay, so the proof continues until we arrive at this inequality. So from here, we can notice that P tau is less than Q tau, which indicates contradiction. Thus, assumption made is wrong. Therefore, the equation can take place for all time before time theta bar. Thus, in whole, we have proved that time theta bar is the optimal pursuit time of the differential game. So this completes the proof. Okay, so in conclusion, we have proved the existence and uniqueness of an infinite first order tree systems of differential equation given by 1.1. And after that, we have solved both control problem as well as pursuit problem in both game 1 and game 2 in accordance to the pursuer's motive. And then in game 3, we obtain the optimal pursuit time of the differential game. Okay, so here are a list of my references. So that's all from me. Thank you.
Right, thank you, Devika. Any question?
Okay, good morning, Devika.
Good morning, Doctor.
Okay, Assalamualaikum warahmatullahi wabarakatuh and to everyone. Just want to know, what is your motivation for this research? Because this is your proposal, is it?
This one is progress, Dr. Hasana.
Progress? Progress, progress, not proposal.
No, not proposal.
Or result.
This one is progress, Dr. Progress means not proposal.
Okay, what is your motivation actually?
Oh, the motivation of my study is first of all to design the infinite first order tree systems of differential equation, and then we prove the existence and uniqueness for the solution of the system. After that, to study the differential game problem defined by the system. So that will be the motivation.
No, you get the problem from, is it continuation from the previous researchers?
Oh, actually for this study, we extended the study into higher dimension because in the literature, in the literature review, so far they only investigated up to infinite first order two systems of differential equation. But for our case, we have developed infinite first order three systems of differential equations. I'm so sorry, the slide is so far. Okay, and it's only up to first order two systems of differential equation, but then in our case, is tree system.
Oh, this is your progress, not your, you already present your proposal.
Yeah, yes, doctor.
Okay, it's okay. Just want to know because you're supposed to be your main objective. What is your main objective?
Oh, my main objective.
How many objectives do you have?
Oh, objective, I got 5, doctor, but then for this case, I only put, where is it? Okay, actually, my objective got another 2 more, but then here you only see 4.
Okay, just
because
you
it's
mentioned
progress.
you mentioned that it is your progress. It's okay lah.
Okay.
I thought your proposal.
Okay.
All right. Any more? Okay. So thank you, Dr. Also Divika. So the next presenter.
Okay, thank you, Doctor.
You're welcome. Shaloof Amal.
Assalamualaikum.
Waalaikumsalam.
Hello, Doctor. I am Amal
Yes.
Shaloof.
Yes, you can try to present.
Okay, just I will share my screen. Is it clear now?
Yes. Control L. Press Control L for full brightness.
Okay. Now? Okay, yeah.
Yes.
Okay, just a minute. Assalamu alaikum. Good morning. I am Amal Shaloof. I am going to present my work about operational matrix method and artificial neural network for solving the fractional differential equation via new derivatives. My supervisor committee, Prof. Dr. Noor Razak bin Samno, Dr. Ali Ahmadi, Prof. Dr. Nick Mohed Hasri Nick Long, Prof. Dr. Sidi Noor Ikmal. This is the outline of my study. Now we are going to give a brief introduction about fractional and fractal calculus. Mathematics is an art of generalization. Fractional calculus is one of these generalizations which nowadays is considered to be the essence of modern calculus. It does not mean the calculus of fraction, neither does it mean fraction of any calculus, differential, integral, or calculus of variation. The fractional calculus is the name of theory of integral and derivative of arbitrary order, which unity and generalize the notation of integer order, differentiation, and inflow integration. Fractal fractional differential equation are very remarkable topics nowadays. The efficiency and power of this fractional differential equation was considered by many researchers in many fields of applications. There are 3 definitions in literature for fractal fractional derivative, which are power law, exponential law, and Taylor law. The natural extension of Lebanese derivative for discontinuous fractal media is the fractal derivative. It is classified as a special local fractional derivative. In recent years, artificial neural network have regarded as an important method for solving a variety of real-world problems due to high learning ability. Artificial neural networks have a lot of advantage, including learning effectiveness and error computation, making this method the preferred choice for solving ordinary partial and fractional differential equation. These definitions are important and related to our work. We start with the Caboto derivative and Riemann integral. Here is the Riemann derivative, and this definition for fractional derivative. You can note that there is extra parameter bar row here. Definition 5 for the fractal fractional derivative in the Caboto sense, and this is for fractal fractional derivative in Riemann sense. Now we consider we have multi-order fractal fractional differential equation presented by equation number 7 with initial condition here, and in equation number 8 we have system of multi-order fractal fractional differential equation with initial condition. Problem statement of this research. Lack of studies in literature deal with the fractal operator, which is focused on the interpretation of real non-local phenomena and the need of to find the new generalized fractal fractional operator and dealing with these modulus as a numerical solution. Using operational matrix and artificial neural networks, which are not mentioned in literature to solve these types of equations, are presented in equation 7 and 8. Scopes of this research. In this research, the main motivation to introduce two new definitions of generalized Caboto and helper fractal fractional operators in fractal domain. Another motivation is that to develop an extension of two methods, which are the operational matrix method and artificial neural network via new types of fractal fractional derivative in fractal domain. Using these new tools, new definitions and methods are defined to solve system and multi-order fractal fractional differential equations. We also investigate the error-bound convergence, accuracy simulation, and some properties of these new methods. Objectives of this study. The first objective to introduce the definition of generalized Caboto fractal fractional operators, then extend the operational matrix of derivative to solve equation 7 and 8. To define the definition of helper fractal fractional operators, and then to focus on solving equation 7 and 8 with operational matrix of derivative. Direct objective to develop an artificial neural network in fractal domain for solving linear and non-linear multi-order fractal fractional differential equation in generalized Caboto fractal fractional derivative for alpha between 0 and 1. Then we derived an artificial neural network in the fractal domain for finding solution of higher linear multi-order fractal fractional differential equation for alpha greater than 1 with variable and constant coefficients. Study accuracy, convergence, error-bound simulation, and some properties of these methods. These some important researches or studies related to our work in fractal and fractional calculus. Here, the most important studies in artificial neural network we use in our study. Shifted Legendre polynomial is defined by this formula on the interval from 0 to 1. If y of t is a square integrable function, we can approximate it by equation number 9, formula number 9, and formula 10 to find the unknown coefficients Ci, Cj. This is the formula to approximate y of t by a shifted Legendre polynomial. Formula number 13 is to define the first derivative of shifted Legendre by using operational matrix, and formula number 15 to find the nth order of shifted Legendre polynomial by using operational matrix. This is the elements of the matrix of operational matrix. Now we are going to define helper fractal fractional operator. We have two steps. Number 1, to define helper fractal fractional derivative operator, then introduce the extension of operational matrix with this new definition. Definition number 7 is new. In this definition, we give the new definition for helper fractal fractional operator of derivative, this formula. Note that in this formula, if we put bar rho equal to 0, we will get the Riemann of a fractal fractional derivative, and if we put bar rho equal to 1, we will get the fractal fractional derivative in the Caboto sense. Theorem 1 to find the derivative of t to power k by using helper fractal fractional derivative. This is the proof of this theorem. Theorem 2 to find the derivative of shifted Legendre polynomial by using operational matrix of order m plus 1. This is the operational matrix. Here is the elements of this operational. Now we are going to apply our method to solve linear multi-order fractal fractional differential equation in formula number 23 with initial condition. We start by approximate y of t by using operational by shifted Legendre polynomial. Then we apply operational matrix of derivative, and we will get a system of algebraic equation, and can solve it by any software, computational software, and we will get a non-coefficient of factor C. After that, y of t will be computed. Now we solve non-linear multi-order fractional differential equation in the formula 32 with initial condition. Also, we start by applying approximate y of t by shifted Legendre polynomial. Then we apply operational matrix on the given equation, and we will get system of algebraic equation, and we solve it to compute y of t. Now we solve a system of linear or non-linear of fractal fractional differential equation. This is the system with different value of alpha and beta. Now with initial condition, we start as before, approximate y1, yt, and ym by shifted Legendre polynomial. After that, we apply operational matrix on both sides, and we will get system of algebraic equation, and we can solve it by any computational software to get y of t. Error bound of this method can be determined by theorem number 3. This is the error bound of our method, and this is the proof. Now we are going to present 5 examples to show the powerful of our method. Example 1 is the Riccati fractional equation with initial condition. We will compare our result to trigonometric basic function. You can see here we choose m equal to 10. This is m, and alpha equal 1, beta 1, and bar rho equal to 1. This is the exact solution. This is absolute error of our proposed method. This is the absolute error of the method in 14, which is a trigonometric basic function. It is clear that our solution is very good and very close to the exact solution. Now, the example 2 is also Riccati fractional differential equation. We will compare our result to 3 methods in literature, representing kernel method and modify homotopy permutation method, and representing kernel Hilbert space method. For m equal to 15, alpha 0.75, beta 1, and bar rho equal to 1, you can see that our result is more close to the exact solution. Also here we put some figures to explain when we choose different values of alpha, bar rho, and beta. Example 3 to solve another type of a fractional problem. It's a problem with alpha equal to 0.5. The classical solution is t to power 1 over 3. Note that the function is not differentiable at t equal to 0. You can see here from the figures where we get the solution with error to 10 to power minus 3. And here is the numerical solution in table 3. Example 5 to solve multi-order fractal fractional differential equation. We choose m equal to 3, apply operational matrix, and then we will get the exact solution. Example 5 to solve system of fractal fractional differential equation with multi-order. Alpha 1 is different from alpha 2, and we compare our result to fractional differential transform method. Table 4 for the numerical solution of y for y of t, and table 5 to present the numerical solution of z of t. Figures show that our solution is more close to the exact solution. Here we change numbers of beta. Note that in order to find out the approximate solution for a given problem by using operational matrix, 4 steps are required. First step, approximate y of t by shifted Legendre polynomial, calculate operational matrix for fractal fractional order and apply it on the given problem and get a system of algebraic equation, calculate a non-coefficient, and then we can calculate y of t. The publications of the article first paper, an efficient operational matrix method for solving fractional differential equation with generalized Caboto type fractional derivative. This paper was published by Mathematics and Computers and Simulation journal. Second article, an iterative technique for solving fractional differential equation based on artificial neural network in the new generalized Caboto sense. This paper was by Engineering with Computers journal, doing the fractional differential equation using operational method. This paper was published by Applied Numerical Mathematics journal. Here some relevant reference related to our work. Thank you.
All right, thank you, Amr. Any question? From Dr. Ni or Professor Nadia atau Dr. Naraza?
Okay, thank you, Dr. Nadiha, and also I'm Shaluf. Okay, thank you for your presentation, and you have a nice plot there. Okay, can you go to the result? Maybe slide 48, I think.
48.
Because you have a plot.
Oh, okay.
Look at the figure. Okay. I just would like to know. Okay, you plot the figure and then you have the result from your presented method. Well, I can see that there's a gap. There's a gap between the solution from the method you propose and the exact solution. Okay, do you think is there any what's the reason? Why the line from your presented method is not close to the exact solution?
Because the alpha is not equal to 1, because alpha is just a minute here. You can see alpha here is 0.7 and 0.9. It is very far from 1. That is the reason.
Okay, so do you know why when if alpha equal 1, the method you propose is able to get very close to the exact solution, but when different alpha, why is it far? Is there any reason?
Because it's like the history. When become close to alpha, we get more good solution, and close to alpha equal to 1.
Yeah, I know, but why the reason?
I don't know, in fact.
What's something that you can improve from the method that you have?
Not related to our method, Prof, because you can see the FDTM, fractional transform method, is a very good method and have good accuracy, but it is related to the problem at itself, not at the method.
I know, but there must be a reason, because the plot doesn't seem like the method that you that is not approaching the exact solution.
No, when I change alpha equal to 1, I get the exact solution.
I know alpha equals 1 will be just an ordinary
yes, because it is
question, so it's not challenging.
Yes, but when I choose alpha, not 0.7, maybe good, more high alpha, I get more good result.
More higher alpha, that means what value?
Now I don't. If you want, I will compute it and send to you, because now I don't have.
Because now maybe I'm not sure.
I already calculate it before. When choose alpha close to 1, it is have good result.
Yes, I know.
But I now choose this result. I choose this alpha 0.7 because I find example in the literature to solve this by the same value. And also I choose it, I find alpha 1 equal to alpha 2, but in this example, I want to show when different value of alpha 1 and alpha 2. If they are the same or the alpha is more close to 1, I get more good results.
Okay, I'm not sure, but it will be interesting if you can find out the reasons why when the alpha is far from 1, so your result is not close to the exact. Maybe it will be something that you can search, because I'm not sure, because in my case, for my student, we study the stability. Then we can have the clear picture why is not the result is not good when the alpha is far from the 1. So in terms of the stability. So I'm not sure in your case, can you do that or not? Okay, and then did you test for alpha greater than 1?
No, because alpha here between 0 and 1.
Okay, but no, because okay, just now in your objective, you said that you also going to solve for alpha greater than 1.
For by another method by artificial neural network, and also for the, just a minute, I will show you here.
Because I think
For,
I saw there are two, this one.
Also, in objective one, I solve for alpha greater than 1, but helper it is alpha between 0 and 1. That is the reason. But for objective 1, I solve for greater than 1, and also in objective 4.
Oh, because I thought that when you mentioned objective number 4, so objective number 4 is just for the multi-order.
All for multi-order from 1 until 4.
Because just now I didn't see for alpha greater than 1. I'm not sure in your
also in paper number 1, Prof, I solve for alpha greater than 1. But helper is the alpha, it is must be between 0 and 1. It is the definition of helper fractional derivative.
Actually, you can go for higher order.
It is, no, because helper is construct between 0 and 1. No, not to change, not more than that. This is the reason why.
Okay, but alpha greater than 1, that means you have to construct another method?
Yes, I construct it here in number 1, also by operational matrix, by generalized Caboto, because we can choose any alpha, and also in number 4, we can choose for any alpha. But for helper, the definition of helper between 0 and 1.
Okay, only that now I think maybe the result when the alpha is far from 1, so Y is not moving closer to the exact solution. That's the question that I can't see in your result. Okay.
All right.
Okay, thank you.
Thank you, Prof. Zanaria. And I think I just may add, that is also a quite interesting comment, because reasons are why we do research. So we need to find the reason why that happened. All right. Also,
thank you,
Amar. Thank you, Amar. And we go for the last presenter, Muhammad Aiman.
Yes, hello, assalamu alaikum.
Wa alaikum salam.
Yes, I'm here and I'm going to share the slides with you. Can you see the slides on your screen?
Yes.
Okay. Okay. So my talk, it is like a talk on Q burst Einstein to controversy operators with some approximation properties. It's like my supervisor is main supervisor at UPM is Professor Adem, and main supervisor at University of Newcastle is Dr. Vishnu. And my co-supervisors are here also, Dr. Siti and Dr. Noraza. So the main purpose of this presentation is to discuss the convergence and other properties of Q Bernstein Cantrobich operators, including real positive number with shifted nodes. The basic Q calculus generates shifted knots of burst and Kentrovich operators. We explore the convergence properties of our new operators in the space of continuous functions and Lebesgue space in particular. The modulus of continuity and the integral modulus of continuity are also used to compute the degree of convergence. Furthermore, we present the development of quantitative Voronov-Kaya type theorems estimates. By implementing the Bernstein polynomials in 1912, Bernstein provided a very short and simple proof of the Weierstrass approximation theorem. Lupas introduced the Q analog of Bernstein polynomials in 1987, and Phillips introduced it in 1997. Since then, several polynomials have been generalized and investigated using Q calculus. Some examples and papers related to our present theme containing Q Bernstein shifted operators, Q Bernstein Kentrovich operators, Bernstein Kentrovich operators based on PQ calculus were introduced by Moselin and others in these papers. So the Bernstein operators have been extended in various ways to approximate functions of various classes by replacing point evaluation functions with some integrals. Bernstein-Kentrovich operators were introduced in 1930 to deal with the approximation in LP space defined on interval closed interval 0, 1, for which Bernstein operators are unsuitable. So, and Bernstein-Dermer operators were introduced 37 years later. So Xiao studied Jackson type estimation by Kentrovich type positive linear operators in LP species in 2013, while Gadzhiev studied weighted LP approximation in 2007. So in 2004, the Stencho variant of Bernstein-Kentrovich operators were defined by Darboso. Like this. Equation 1, inequality 1, or equality over. And while these operators with shifted knots were studied by Gadzhiev, for the operators, here we have moments here and also shifted knots here. So Suku and others introduced the Bernstein to Kentrovich operators with shifted knots by this. So here we see that we have introduced the Bernstein to Kentrovich operators using shifted knots involved by Q integers and other basic aspects of Q calculus. Using of shifted knots of real parameters has certainly some advantage in approximation theory, as we can do some approximation on some interval as well as sub-intervals. Some basic results for approximation as well as rate of convergence of the introduced operators are established. We obtain the degree of approximation of our newly obtained or newly generated operators by using the modulus of continuity and integral modulus of continuity. We also give some direct theorems in LP spaces, and so we will start with some basic aspects of Q calculus. Q calculus is a very useful tool and a very fruitful connection between maths and physics. So we will start with the definition of Q numbers. So here the Q numbers is defined by this. Here we have taken theta as non-zero complex number. Here for it is 1 for the case where theta is 0, and third is the case for theta is a natural number. And then we can see the definition of Q factorial for the two cases, for theta equal to 0 and theta as a natural number. Now we take Q as any complex non-zero on any complex number excluding 0 and 1, and the Q binomial is then Q binomial coefficient is then defined by this, and the Q analog is defined by this. And for the two condition where one condition is like when R and S are both natural numbers, and the second being where R and S are both 0. So the Q-Jackson integral, it is defined by this on the interval, closed interval AB. It was defined by Jackson, obviously. So we will proceed to the fundamental theorem of Q calculus, which is very important in Q calculus. We take phi b anti-Q derivative of the function f, and then it is defined like this: the derivative of f okay. So we will now proceed to the construction of operators, which is the main work did by us. So in this section, we are taking the operators introduced by Dorboso and Kondrovich. And we will construct the new operators, which will be the more generalized form of the previously generated operators. Okay. So here we are also taking the shifted knots, and as we can see, here are the shifted knots. So we will define our operators for in LP space, and now we have defined by our new operators by equation 9, and here we can see if we take Q equal to 1, it will be more like without the involvement of Q calculus, and if we take mu2 equal to 0 and mu1 mu2 all equal to 0, then the operators are reduced to the classic burst and Kondrovich operators here defined here. So we have introduced the generalized form of these operators given in equation 1. Okay, so we will proceed with the lemma, and here we have some test functions. Test functions is for j equal to 0, 1, 2, and test functions are eta j. So for test function and j where j is equal to 0, we have the first like moment here defined by this 0.1, and the second moment here is this. The third moment is much bigger, taking up the whole slide. So now further on, we will calculate the central moments, which are necessary. And we have only just calculated 2 moments because the third one will take much more space, and it was of no use right now. So we calculate just 2 central moments. Second was taking 2 slides, so I think a minimum 5 slides. So so it was mentioned that the integral operators defined by Q-Jackson integral are linear but may not remain positive. So to overcome this problem, the function f must be strictly monotonic increasing. So here we will take f to be the strictly monotonic increasing function, and we will define like this. Let's proceed to more useful results because we have this time. Okay, so we are taking a sequence of positive linear operators from a space of continuous function to a space of another space of continuous function. And then if we're taking a function from this space, then we have this defined by this, and okay, okay, this theorem is for the global global estimation, and this theorem is for local estimation. Okay, we have applying some P3K functional using quantitative estimates, and next we are here seeing the relation between P3K functional and the integral modulus continuity given by inequality 14. Okay. So more interesting thing is now the graph. Here we are taking the function x square xi square plus 1 and taking some fixed values for mu1 mu2 and mu1 mu2, and we are varying r here. So we can see here the dotted line is the original function, and the blue, green, and red line are for different values of r. We are taking these values in our newly formed generalized linear operators. Let me show you that again in the equation 9. So here we are taking the fixed values of mu1, mu2, and mu1, mu2 here, and we are varying r. Obviously, we will keep this q like this only because we are talking about q calculus, the all values of q except 0 and 1. So we are only varying r here, and as we can see, that if we are increasing r, we are coming more closer to the function, the original function, which is x squared plus 1. And we can do one more thing in this, is that we can form a new graph and compare the generalized, which is like developed by us, the generalized operators and the old operators, and we can compare whose approximation is better graphically. And here are some of our publications in 4 semesters, in 5 semesters, and 2 are under minor reviews. Let's see what happens here. Okay.
All right. Thank you. So any question from the audience or supervisor? Okay. So I think there will be no question.
Okay.
Dr. Nadiha?
Yes, yes.
I just wonder, for the objective, have you fulfilled all the objective, Mr. Aiman?
We are currently working like one of them is like calculating errors in all our publications. Errors for the positive linear operators we have developed in all our publications. So maybe preparing another paper or another report for the errors, the error-based report.
meaning that all the objectives has been fulfilled, is it?
Almost.
Okay, maybe I just some advice, because when you're presenting, we are giving marks, right? So maybe next time you can put all your objective, your literature review, and your main result, and so on. Yeah.
Okay.
Okay. Thank you.
Sure. Thank you.
May I ask one question also?
Yes,
Yes,
sure.
Ayman, can you make this kind of programming using the either MATLAB or Maple, but not particular for the functions? You generalize it, and when you put input as an input function, for example, it will work out for you.
Okay.
At the moment you are working and using the MATLAB to support your examples, but I am asking further than that.
Okay.
Did you get me?
Yes.
Okay.
The generalized
Okay,
programming you want.
yes, correct. Yes. For example, at that time you will enter your input either as a function or as an operator. Then you will work out and get the result.
Okay.
Like automation for your study.
Yes. I have the programming like this only. Just I have to change the function and not the other settings. I just have to change the function.
But maybe you need to put the coding that one rather than the examples.
Yes.
Okay.
Yes.
Okay. Thank you.
Yeah.
Okay, thank you, Prof. Adam, Dr. Fazila, and also our last presenter, Muhammad Aiman. Okay, before we depart today, so I would like to remind you that supervisor and also external evaluator and also co-supervisor to submit your evaluation form to Dr. Siti Mahani. And also, I would like to remind you, the evening slot will start at 2:30 p.m. So please be on time. Okay, that's all for half of our day, and see you in the evening, in the afternoon. Sorry.
Okay, thanks everybody.
Inshallah. Assalamu alaikum.
Alaikum salam. Alaikum assalam.
Good afternoon.